Welcome back to Space Historian. Tonight we're going to explore one of the most ambitious aeronautical programs you've probably never heard of. It's a story about the persistent dream of flying faster than sound without disturbing the peace below. It's about brilliant minds, cutting-edge technology, and a demonstration flight that would finally prove what scientists had theorized for decades. This is the story of the quiet supersonic platform. Picture this. It's August 27th, 2003, and the sun is rising over Edwards Air Force Base in California. The same stretch of desert where Chuck Yeager first broke the sound barrier nearly 56 years earlier is about to witness another milestone in aviation history. A modified F-5E fighter jet with an oddly elongated nose sits ready on the runway. Nearby, a NASA F-15B chase plane prepares to follow. On the ground below the planned flight path, 42 sensors and recording devices are arrayed across 2.5 miles of desert. Engineers, scientists, and test pilots from DARPA, NASA, Northrop Grumman, and various research institutions have gathered. They're all here for one purpose: to prove that an aircraft can be shaped to reduce the intensity of its sonic boom as it travels through the atmosphere. This wasn't just another test flight. This was the culmination of theoretical work that had begun decades earlier, of dreams that had been deferred, of programs that had been cancelled, and of a persistent belief that the sonic boom problem could be solved. The modified aircraft they called the Shaped Sonic Boom Demonstrator was about to attempt something that had never been proven in actual flight conditions through a real atmosphere. If successful, it would validate theories developed in university research labs and open the door to a new generation of supersonic aircraft that could fly over land without causing the disruption that had grounded commercial supersonic flight for more than 3 decades. But to understand why this moment mattered so much, we need to go back. We need to understand the sonic boom problem, the dreams of supersonic passenger flight, the regulatory barriers that arose, and the long road of research and development that led to this August morning in 2003. We need to understand why DARPA, the Defense Advanced Research Projects Agency, initiated a program called the Quiet Supersonic Platform, and how that program brought together military needs, civilian aspirations, and cutting-edge aerospace technology in a unique collaboration. The story of the Quiet Supersonic Platform is more than just a tale of aircraft design and flight testing. It's a story about the intersection of physics, engineering, economics, and public policy. It's about the challenge of making supersonic flight socially acceptable, not just technically feasible. It's about the difference between what's possible in theory and what can be achieved in practice. And it's about the persistent human drive to go faster, to shrink distances, to make the world smaller through speed, while still being good neighbours to the people below. Over the next 2 hours, we're going to take a deep journey into this fascinating chapter of aviation history. We'll meet the scientists who developed the theoretical foundations. We'll explore the programs that came before, both successful and failed. We'll see how defense research intersected with commercial aviation dreams. We'll watch as multiple aerospace giants competed and collaborated simultaneously, and we'll witness the moment when theory finally met reality in the skies over Edwards. So settle in, get comfortable, and let's begin our exploration of the Quiet Supersonic Platform, a program that dared to challenge one of aviation's most intractable problems. The Thunder Problem: Understanding the Sonic Boom Challenge. When Chuck Yeager first broke the sound barrier in the Bell X-1 on October 14, 1947, he ushered in a new era of aviation. Suddenly, the sky wasn't limited by the speed of sound anymore. Within a decade, supersonic fighters were becoming commonplace in military air forces around the world. Engineers and visionaries began dreaming of passenger planes that could cross oceans in half the time of conventional aircraft. The The supersonic age seemed full of promise, but there was a problem, and it was loud. Every object moving through the air creates pressure waves. At subsonic speeds, these waves propagate ahead of the object, gently pushing air molecules out of the way. But at supersonic speeds, the object moves faster than these pressure waves can travel. The result is a shock wave, a sudden, sharp change in pressure that travels along with the aircraft like the bow wave of a boat cutting through water. When these shock waves reach the ground, they create what we call a sonic boom. The sonic boom isn't a single event that happens when an aircraft breaks the sound barrier. That's a common misconception. The boom is continuous as long as the aircraft maintains supersonic speed. It lays down what's called a boom carpet along the entire flight path, typically about 1 mile wide for each 1,000 feet of altitude. Everyone within that carpet experiences the boom as the aircraft passes overhead. The characteristic shape of a sonic boom pressure signature is called an N wave. If you were to graph the pressure changes over time as a boom passes, you'd see a sudden sharp increase in pressure at the front shock, followed by a gradual decline to below normal atmospheric pressure, then another sharp increase back to normal at the rear shock. The shape resembles the letter N, hence the name. These sudden pressure changes, particularly the initial shock, are what create the loud bang that people hear and feel. For military aircraft flying in designated training areas or over unpopulated regions, sonic booms were accepted as a necessary part of operations. The benefits of supersonic flight for defense purposes outweighed the noise concerns. Fighter pilots training over remote deserts or vast oceans could fly as fast as their aircraft allowed. But for civilian aviation, especially over populated areas, the sonic boom quickly became an insurmountable problem. During the 1950s and into the 1960s, as more supersonic military aircraft entered service, sonic booms became increasingly common over American communities. The Air Force operated B-58 Hustlers, the nation's first supersonic bomber, from bases in Texas and Indiana. These sleek delta-wing bombers cruised at Mach 2, and their sonic booms rattled windows, cracked plaster, and terrified people who didn't understand what was happening. Complaint letters flooded into congressional offices. Claims for damage to property accumulated. Public relations became a significant problem. The experience with the B-58 and other supersonic military aircraft provided an early preview of the challenges that would face any attempt to operate supersonic passenger planes over land. The booms weren't just annoying. They could startle people, disrupt sleep, interfere with work, and cause actual physical damage to buildings, particularly older structures. Studies showed that peak overpressures of more than 1 pound per square foot could shatter windows and cause structural damage. Even lower pressures, in the range of 0.5 to 1.0 pounds per square foot, generated numerous complaints and created vibrations that people found disturbing indoors. Yet despite these problems, the dream of supersonic passenger flight persisted. In the early 1960s, both Britain and France, as well as the Soviet Union and the United States, launched programs to develop supersonic transport aircraft. The promise was tantalizing. Imagine crossing the Atlantic in 3.5 hours instead of 7. New York to London in the time it took to watch a double feature at the movies. The Pacific reduced from a tedious 14-hour ordeal to a manageable 7 hours. Business executives could attend meetings on another continent and return home the same day. The world would truly shrink. The British and French, recognizing the enormous costs involved, pooled their resources and created the Concorde program. The Soviet Union developed the Tupolev Tu-144. And in the United States, President John F. Kennedy announced in 1963 that America would build a supersonic transport that would be superior to anything else in the skies. Boeing and Lockheed competed for the contract, with Boeing's 2707 design eventually winning. The American SST, as it was called, was planned to be larger and faster than the Concorde, capable of carrying 300 passengers at Mach 2.7. But as these programs progressed, the sonic boom problem loomed larger and larger. It became clear that no existing technology could eliminate or sufficiently reduce the boom to make overland supersonic flight acceptable. The laws of physics seemed immutable. A supersonic aircraft of any size would generate shock waves, and those shock waves would create sonic booms that disturbed people on the ground. The Concorde program moved forward, but with the understanding that the aircraft would only fly supersonically over water. Overland routes would require subsonic cruise, negating much of the aircraft's advantage. The economic implications were sobering. If supersonic transports could only fly supersonic over oceans, their utility was severely limited. The primary routes would be transatlantic and transpacific. Domestic flights across the United States or Europe would gain no benefit from supersonic capability. In the United States, opposition to the SST program grew. Environmental groups raised concerns about noise pollution and potential effects on the upper atmosphere. Economists questioned whether the enormous development costs, estimated at over $3 billion in 1970 dollars, could ever be recouped. Communities along potential flight paths protested the prospect of regular sonic booms. The debate became increasingly political and contentious. Finally, in March 1971, the United States Senate voted to terminate funding for the SST program. The Boeing 2707 never flew. It remained a wind tunnel model and a collection of engineering studies. The decision was based on multiple factors: environmental concerns, economic doubts, and the sonic boom problem. Without a solution to the boom, the aircraft would be restricted to overland subsonic flight, greatly reducing its economic viability. The benefits didn't justify the costs, particularly when the aircraft couldn't use its full capabilities over populated areas. The Concorde and Tu-144 did eventually fly. The Concorde entered service in 1976 and flew commercially until 2003, a remarkable 27-year service life. But both aircraft proved the skeptics right about economics. Neither ever came close to recouping their development costs, which were largely borne by their respective governments. The Concorde fleet consisted of just 20 aircraft, of which only 14 entered commercial service. British Airways and Air France operated a small fleet between them, flying limited routes where supersonic flight over water was possible. The experience was sobering. The Concorde demonstrated that supersonic passenger flight was technically achievable. The aircraft was remarkably reliable and had an excellent safety record until the tragic accident in 2000. Passengers loved the speed and the prestige, but economically it was a failure. The aircraft burned fuel at several times the rate of a Boeing 747 per passenger mile. Ticket prices were exorbitant, limiting the market to wealthy individuals and business travelers on expense accounts. The operational economics only worked because the airlines had essentially been given the aircraft for free by their governments, and critically, the Concorde's sonic boom meant it could never fly supersonically over land. The aircraft typically accelerated to supersonic speed after leaving coastal areas, then maintained that speed over the ocean, decelerating before making landfall on the opposite shore. This restriction limited route options and operational flexibility. Proposals for supersonic corridors over remote areas went nowhere due to public opposition and regulatory resistance. By the 1970s, the sonic boom had effectively killed commercial supersonic flight over land. The United States Federal Aviation Administration formalized this reality by implementing regulations that prohibited civil aircraft from flying supersonically over US territory. Similar restrictions were adopted by other countries. The boom barrier seemed absolute, yet research continued. Scientists and engineers refused to accept that the problem was completely insoluble. If the boom couldn't be eliminated, perhaps it could be reduced to acceptable levels. Perhaps the shape of the pressure signature could be changed. The sharp N wave transformed into something gentler. Perhaps smaller aircraft would generate weaker booms that could be tolerated. Throughout the 1970s, 1980s, and 1990s, various researchers and programs investigated these possibilities. The economic stakes were significant. The global market for air travel continued to grow rapidly. Business travelers valued time above almost all other factors. The premium that customers would pay for cutting flight time in half was substantial. If a way could be found to make the sonic boom acceptable, a new market for supersonic aircraft could open up, potentially worth hundreds of billions of dollars over several decades. The rewards were enormous, but so were the technical challenges. The sonic boom problem had multiple dimensions. It wasn't just about making the boom quieter, though that was certainly part of it. The boom also had to be acceptable indoors, where structural vibrations could amplify the effect. It had to be acceptable repeatedly, day after day, as aircraft flew regular schedules. It had to be acceptable across different weather conditions and atmospheric states. And it had to be acceptable not just to engineers and scientists with meters and equations, but to ordinary people going about their daily lives. Understanding exactly what would be acceptable to the public became its own research challenge. How loud was too loud? What boom characteristics were most annoying? Did the shape of the pressure signature matter as much as its overall intensity? Were there ways to reduce indoor vibrations separately from outdoor noise? NASA and other organizations conducted surveys and studies, trying to quantify human response to sonic booms of different characteristics. The results suggested that acceptability wasn't just about peak pressure, but about how quickly the pressure changed and how long the boom lasted. This was the landscape when Richard Seebass, a brilliant aerodynamicist at Cornell University, began developing theoretical approaches to sonic boom minimization in the 1960s. And it was the landscape that would eventually lead to DARPA's Quiet Supersonic Platform program decades later. The dream of supersonic flight over land hadn't died. It had merely been deferred, waiting for the right combination of theory, technology, and determination to make it reality. The Professor and the Theory. Richard Seebass's contributions. In the pantheon of aerospace pioneers, Richard Seebass doesn't have the name recognition of Chuck Yeager or Wernher von Braun. He never piloted an experimental aircraft or directed rocket launches, but his contributions to understanding and potentially solving the sonic boom problem were profound and enduring. His work would form the theoretical foundation for efforts that would continue long after his death, ultimately culminating in the flight demonstrations of the Quiet Supersonic Platform program. Richard Seebass was born in 1936 and came of age during the early jet age, when aerospace engineering was exploding with new possibilities. He pursued his academic career at Cornell University, where he eventually became a professor and researcher in the Sibley School of Mechanical and Aerospace Engineering. His expertise was in fluid dynamics, specifically the complex behavior of shock waves and supersonic flow. These were precisely the phenomena that created sonic booms, making him ideally positioned to tackle the problem. In the late 1960s, as the American SST program was moving forward and the sonic boom issue was becoming increasingly critical, Seebass began working with his colleague Albert George on a theoretical approach to boom minimization. Their collaboration would prove remarkably fruitful, producing insights that remained relevant for decades. The fundamental insight of Seebass and George was that while the sonic boom couldn't be eliminated, it might be minimized through careful aircraft shaping. Every aircraft generates shock waves from various parts of its structure: the nose, the wings, the engine inlets, the tail. These shock waves propagate downward through the atmosphere, and as they travel, they can merge and strengthen, eventually reaching the ground as the characteristic N-wave boom. But what if the aircraft could be shaped so these shock waves didn't coalesce as strongly? What if the pressure signature could be modified to produce a less intense boom? In 1971, Seebass and George published a landmark paper in the AIAA journal titled Sonic Boom Minimization, including both front and rear shocks. This paper laid out a mathematical framework for designing aircraft shapes that would produce the minimum possible sonic boom for a given weight, length, and flight condition. Their work wasn't about eliminating the boom, the laws of physics made that impossible, but about finding the optimal configuration to minimize its intensity. A key concept they developed was what became known as the figure of merit for sonic boom levels. This was essentially a way to characterize how loud a boom would be based on the aircraft's weight and length. The formula showed that the minimum achievable sonic boom over pressure was related to the aircraft's weight divided by its length raised to the 3/2 power. This meant that for a given weight, making the aircraft longer would reduce the boom intensity. Conversely, for a given length, reducing weight would help. But the relationship wasn't linear. Length was more powerful than weight in the equation. Using this figure of merit, Seebass and George could evaluate different aircraft designs. They calculated values for the Concorde and found a figure of about 1.4. For the proposed Boeing 2707, it was around 1.9. They suggested that values of about 1.0 or lower would be needed for a boom to be potentially acceptable to the general public. These numbers provided quantitative guidance for designers and made clear just how challenging the problem was for large supersonic transports. But Seebass and George went further. They described what an optimized sonic boom signature would look like. Instead of the sharp N wave with its sudden pressure spikes, they theorized a flat-topped signature. In this idealized waveform, the initial pressure rise would be more gradual. The peak pressure would be sustained for a longer period, and the final return to normal pressure would also be gradual. This spreading out of the pressure changes over time would make the boom less startling and less likely to cause structural vibrations, even if the total energy in the boom remained significant. Creating such a signature would require extraordinarily precise control over the aircraft's shape. Every part of the aircraft contributes to the near-field pressure distribution around the plane. As these pressure disturbances propagate downward through the atmosphere, they evolve and can merge. Getting them to arrive at the ground in a flat-topped configuration rather than as sharp N waves would require the initial near-field signatures to be very carefully tailored. It was an incredibly complex multi-dimensional optimization problem. Seebass continued working on sonic boom theory throughout the 1970s and 1980s. He moved to the University of Arizona, where he continued his research. Later, he became chair of the Department of Aerospace Engineering Sciences at the University of Colorado at Boulder, where he built a strong program in supersonic aerodynamics. Throughout these years, he refined and extended his theoretical work, always with an eye toward practical application. By the 1990s, as NASA's high-speed research program was examining the feasibility of a new supersonic transport, Seebass's work gained renewed attention. The HSR program was looking at a 300-passenger Mach 2.4 aircraft, similar in concept to the Boeing 2707 that had been cancelled decades earlier. As the program progressed and accumulated technical findings, it became increasingly clear that such a large aircraft would face insurmountable sonic boom problems. Even with the most advanced shaping techniques, a plane that large and heavy couldn't achieve a figure of merit anywhere close to 1.0. This realization led Seebass and others to consider an alternative approach: smaller supersonic aircraft. The weight term in the sonic boom equation was crucial. A business jet carrying 8 to 10 passengers might weigh 60,000 to 100,000 pounds, compared to 700,000 pounds or more for a large supersonic transport. That factor of 7 or more in weight, combined with the possibility of making the smaller aircraft relatively long and slender, could potentially bring the figure of merit down into the acceptable range. In November 1998, as the HSR program was winding down, Seebass presented 2 papers at NATO's von Karman Institute in Belgium. These presentations represented his mature thinking on commercial supersonic flight and sonic boom minimization, incorporating decades of research and the latest findings from the HSR program. His conclusions were both pessimistic and optimistic. Pessimistic about large supersonic transports, but optimistic about smaller supersonic business jets. Regarding large SSTs, Seebass was blunt. The economics had never worked for the Concorde despite government subsidies. The technical challenges remained immense. The sonic boom problem seemed intractable for an aircraft of that size. He noted that generating sufficient passenger loads to justify a large SST would require overland supersonic routes from many airports. But solving the acoustic issues for such an aircraft appeared beyond current technology. The boom from a 300-passenger Mach 2.4 aircraft would be simply too intense to allow overland flight. Engine noise was another major problem. The HSR data indicated that adequate sound suppression for takeoff and landing would add about 6,500 pounds per engine, equivalent to the weight of 90 passengers. Variable cycle engines that could switch between high bypass ratio for quiet takeoff and low bypass ratio for efficient supersonic cruise might be needed, but such engines were still largely theoretical. Even if the sonic boom could somehow be addressed, the engine noise issue alone posed a serious challenge. But for smaller supersonic business jets, Seebass saw real possibility. A properly designed SSBJ, he argued, could have a sonic boom quiet enough to be nearly inaudible outdoors and hardly discernible indoors. The key advantages of smaller aircraft weren't just about the weight equation. Smaller aircraft would also benefit from what he called vibrational relaxation effects. Larger aircraft generate sonic booms with significant energy at the frequencies that cause structural vibrations in buildings. These vibrations are what make booms particularly annoying indoors. But much smaller aircraft, with their weaker shock waves, produce booms with less energy at these problematic frequencies. The shock waves from a small, slender supersonic airplane could be so weak that they would contain minimal energy at the frequencies important for structural response and indoor annoyance. Seebass posed a specific hypothetical question: could a 100-foot-long Mach 1.6 supersonic business jet, cruising at 40,000 feet and weighing 60,000 pounds, have an acceptable sonic boom? His analysis suggested yes. With careful shaping to produce an optimized pressure signature, such an aircraft might achieve an overpressure as low as 0.3 to 0.4 pounds per square foot. At that level, the boom could be nearly inaudible outdoors and hardly noticeable indoors. Moreover, business jets didn't follow scheduled routes like airliners. They flew point to point based on customer demand, often to smaller airports. This meant they wouldn't create the repetitive sonic booms that would occur with scheduled supersonic airline service. The lack of repetition might make certification easier and public acceptance more likely. An occasional quiet boom would be far less problematic than dozens of booms per day from scheduled airline operations. Seebass also noted that supersonic business jets would have a significant market if they could be certified for overland flight. The corporate jet market had been growing rapidly throughout the 1990s. Wealthy individuals and corporations were willing to pay premium prices for aircraft that offered convenience, privacy, and time savings. A supersonic business jet that could cut transcontinental flight times in half while still being able to operate over land would find eager customers, even at a price point of $50 to $100 million per aircraft. These 1998 presentations by Seebass helped set the stage for what would become the Quiet Supersonic Platform program. His analysis made clear that small supersonic aircraft were the most promising path forward for civilian supersonic flight. His theoretical work provided the foundation for aircraft shaping techniques, and his vision of a certification pathway through reduced boom intensity and non-scheduled operations offered a potential route around the regulatory barriers that had stymied supersonic flight for decades. Tragically, Richard Seebass wouldn't live to see his theories tested in flight. In November 2000, just as DARPA was awarding the initial contracts for the QSP program, Seebass passed away at the age of 64. He had devoted much of his career to understanding and solving the sonic boom problem. His work had influenced generations of researchers and shaped the direction of supersonic aircraft development. The shaped sonic boom demonstration that would fly in 2003 was built directly on the theoretical foundation he had constructed. But before we get to that demonstration, we need to understand what happened in the years between Seebass's early work and the QSP program. We need to explore the various attempts to design supersonic business jets, the lessons learned from those efforts, and the technological developments that made the QSP possible. The road from theory to practice was neither straight nor smooth. Dreams deferred, early supersonic business jet proposals. The idea of a small supersonic jet for civilian use wasn't new when Richard Seebass began advocating for it in the 1990s. In fact, various organizations had been exploring the concept for decades. Between 1963 and 1995, there were at least 22 different studies or projects focused on developing small supersonic civilian airplanes. These efforts came from universities, aircraft manufacturers, and NASA itself. Most went nowhere, but they accumulated knowledge and identified both opportunities and challenges. The appeal of a supersonic business jet was obvious. The corporate aviation market was growing rapidly. Business jets offered flexibility, privacy, and direct routing that commercial airlines couldn't match. Adding supersonic speed to these advantages would create a compelling product for a wealthy clientele that valued time above almost everything else. If the technical and regulatory challenges could be solved, the market potential seemed substantial. One of the earliest serious SSBJ studies came from Fairchild Swearingen, a Texas-based aircraft manufacturer known for its regional airliners and business aircraft. In the mid-1980s, Fairchild launched a feasibility study involving several major airframe and engine manufacturers. The company developed preliminary designs for 4 different two-engine configurations, all with a range of 4,000 nautical miles and the ability to cruise subsonically as well as supersonically. The proposed engines were modified versions of the Concorde's proven Rolls-Royce Snecma Olympus 593, which had demonstrated reliable supersonic operation. But by 1985, the Fairchild Swearingen project had run into insurmountable problems. Weight projections kept growing as engineers grappled with the realities of supersonic flight. The engines were too loud to meet the FAA's Stage 3 noise restrictions for takeoff and landing. And of course, the sonic boom remained a barrier to overland operations. Without a solution to these problems, the business case fell apart. The company quietly shelved the project. Meanwhile, Gulfstream Aerospace, which had established itself as a leader in the high end of the executive jet market, began its own SSBJ studies in 1988. Gulfstream's reputation was built on long-range capability, comfort, and reliability. The company saw a potential opportunity to extend its brand into supersonic flight. The initial Gulfstream SSBJ concept was substantial: 125 feet long, 100,000 pounds gross weight, Mach 1.5 cruise speed, with ogive delta wings. In an early attempt at sonic boom minimization, Gulfstream's designers managed to reduce the predicted overpressure from 1.0 pounds per square foot to 0.6 pounds per square foot, but only by accepting increased wave drag. The end of the Cold War in 1989 created an unexpected opportunity for international collaboration. The Soviet Union's defense industry was suddenly desperate for hard currency and foreign partnerships. The Sukhoi Design Bureau, famous for its supersonic fighters, had been studying its own SSBJ concept called the Su-51. At the 1989 Paris Air Show, Sukhoi's chief designer and Gulfstream's chairman agreed to explore joint development, combining Sukhoi's supersonic fighter expertise with Gulfstream's business jet experience. The Sukhoi-Gulfstream collaboration designated the S-21 project aimed high. The target was Mach 2 cruise speed with a range of 4,000 nautical miles. The design featured a 114-foot-long airframe with cranked arrow wings similar to those on the F-16XL. Joint teams worked on the configuration through the early 1990s, with Sukhoi's engineers in Moscow coordinating with Gulfstream's team in Savannah, Georgia. It was an unusual partnership, bringing together former Cold War adversaries in pursuit of civilian supersonic flight. But the S-21 project faced the same fundamental problems that had plagued other SSBJ efforts. Weight versus performance requirements proved impossible to satisfy with existing technology. Engine noise remained problematic despite exploring various variable cycle and ejector mixer designs. And the sonic boom, while potentially lower than larger aircraft due to the smaller size, was still too intense for unrestricted overland operations. By 1992, Gulfstream withdrew from the partnership. The company concluded that a concerted effort by the FAA, NASA, industry, and academia would be needed to solve the sonic boom acceptability problem. Without such an effort and without breakthroughs in engine technology, the SSBJ wasn't viable. Sukhoi continued some work on the design for several more years, hoping to find another partner, but eventually that effort too faded away. During this same period, NASA conducted its own series of SSBJ studies. Between 1977 and 1986, Langley Research Center sponsored 8 different projects examining small supersonic aircraft concepts. These weren't development programs aimed at building actual aircraft, but rather technology studies exploring what might be possible and what technologies would be needed. The most extensive of these NASA studies came from Kentron International, a technology contractor working with Langley. Starting in 1981, Kentron performed 4 separate SSBJ concept studies over a 5-year period. Each study incorporated the latest technology assumptions and represented the state-of-the-art at that time. Together, these studies documented both the progress being made and the stubborn persistence of the core challenges. The first Kentron study in 1981 examined an 8-passenger, 2-engine Mach 2.7 business jet with a droop nose similar to the Concorde's. The design assumed advanced titanium and superplastically formed diffusion-bonded materials to reduce weight. A scaled-down version of the GE21/J11 variable cycle turbofan engine would provide propulsion. The aircraft's gross weight was projected at 64,000 pounds with a range of 3,200 nautical miles. But the sonic boom overpressure was calculated at 1.0 pounds per square foot at the start of cruise, dropping to 0.7 pounds per square foot as fuel was burned off. These levels would prohibit overland supersonic operations under any reasonable regulatory framework. The 1983 Kentron study aimed to reduce weight by using more fuel-efficient turbofan engines, minimizing the passenger compartment to barely accommodate 8 people and eliminating the co-pilot to save weight. The result was a smaller aircraft, just 103 feet long, with an arrow wing configuration, weighing only 51,000 pounds at takeoff. The reduced weight helped somewhat with the sonic boom, and the designers hoped that low wing loading and a modified flight profile might alleviate the boom problem sufficiently for cross-country flights. As a backup, the aircraft could fly 2,700 nautical miles at Mach 0.9 when supersonic operation wasn't permitted. For their 1984 study, the Kentron team explored a more radical idea: variable sweep wings. Such adjustable wings had been used successfully on military aircraft like the F-111 and the F-14, allowing optimized performance at both low and high speeds. For a business jet, variable sweep could eliminate the need for a droop nose by allowing better low-speed performance. The 1984 design was 114 feet long, weighed 64,500 pounds, and featured wings that could swing from a swept-back position for supersonic cruise to a less swept position for takeoff and landing. But variable sweep wings brought their own problems. The mechanism added significant weight and complexity. Despite hopes that lighter materials and improved flight control systems would make them practical, further analysis showed the concept was probably too heavy and too expensive for a business jet. Still, the study was valuable in exploring the design space and understanding the trade-offs. The sonic boom remained problematic, with overpressures ranging from 0.9 to 2.0 pounds per square foot, depending on speed, altitude, and aircraft weight. The final Kentron study in 1986 took a different approach. What if the SSBJ could also serve as a military interceptor? This dual-use concept might expand the potential market and justify the enormous development costs. The design was essentially a militarized version of the earlier concepts, capable of carrying missiles and operating in an air defense role. With a gross weight of around 61,600 pounds and low bypass ratio turbofan engines, it would have a range of more than 3,600 nautical miles in civilian configuration, or a combat radius of more than 1,600 nautical miles in military configuration. Even this dual-use concept couldn't escape the sonic boom problem. By flying an optimized climb and acceleration profile, the designers calculated an overpressure of about 1.0 pounds per square foot, still too high for overland civil operations. The aircraft could cruise transonically at Mach 0.96 for nearly 3,800 nautical miles when needed, but this defeated much of the purpose of having a supersonic aircraft. Beyond these formal studies, various aircraft manufacturers continued to explore SSBJ concepts through the 1990s. In France, Dassault Aviation, maker of the successful Falcon business jet line, studied a supersonic version in the mid-1990s. The proposed Falcon SST would have been powered by 3 non-afterburning engines and capable of Mach 1.8. The company invested several $1 million in the concept before cancelling it in 1999 when no suitable Stage 3 compliant engine could be found. In Japan, aerospace researchers worked on designs that could cross the Pacific Ocean supersonically, a particularly attractive capability for a nation separated from most of the world by vast oceanic distances. Japanese engineers explored concepts for supersonic transports ranging from small business jets to larger airliners. These efforts produced valuable research findings and advanced computational methods, but no actual development programs. Perhaps the most intriguing SSBJ work during the 1990s was happening behind closed doors at Lockheed Martin's legendary Skunk Works. The Skunk Works, officially named the Advanced Development Company, had produced some of aviation's most remarkable aircraft: the U-2 spy plane, the SR-71 Blackbird, and the F-117 stealth fighter. In the mid-1990s, the Skunk Works became interested in low sonic boom technology, seeing potential applications for both military reconnaissance aircraft and civilian supersonic jets. The Skunk Works hired John Morgenstern, who had been McDonnell Douglas's lead sonic boom analyst during the high-speed research program. Morgenstern and his colleagues began developing techniques for shaping sonic booms through careful aircraft design. They explored novel ideas like specialized control surfaces near the nose that could be extended to reduce shockwave strength. These efforts were largely classified, as the military applications were sensitive, but hints of the work began appearing in patent applications. To deepen their expertise, the Skunk Works also brought in Richard Seebass as a consultant. His theoretical knowledge combined with Lockheed Martin's practical engineering experience created a powerful synergy. By 1998, Lockheed Martin felt confident enough in their sonic boom work to team up with Gulfstream to explore low-boom SSBJ development. Gulfstream brought their business jet expertise and market knowledge, while Lockheed Martin contributed advanced aerodynamic shaping techniques. This partnership was particularly significant because it represented a coming together of two very different organizational cultures. Lockheed Martin's Skunk Works operated in a world of classified military programs, working on bleeding-edge technology with virtually unlimited budgets for critical defense needs. Gulfstream lived in the commercial world, where market demand, production costs, and regulatory certification drove every decision. The combination had the potential to produce something neither could achieve alone: a militarily valuable capability that could also be commercialized. By the late 1990s, several factors were converging to make a serious SSBJ development effort seem possible. The corporate jet market was booming, growing about 400% from 1995 through 2000. Much of this growth came at the expense of first-class and business-class airline travel, as executives and wealthy individuals sought more direct, private, and flexible transportation. The market was moving upscale, with more customers buying larger, longer range, and more expensive aircraft. Computational capabilities had advanced dramatically. Sonic boom prediction, once possible only through laborious wind tunnel testing and limited mathematical models, could now be done using sophisticated computational fluid dynamics. Engineers could evaluate thousands of design variations on computers, rapidly iterating toward optimized configurations. This made Richard Seebass's theoretical approaches practical in ways they hadn't been in the 1970s and 1980s. Materials technology had also progressed. Advanced composites offered the possibility of lighter, stiffer structures. New alloys could withstand higher temperatures while maintaining strength. Manufacturing techniques like superplastic forming could create complex shapes more economically. All of these advances made it more feasible to build the long, slender, precisely shaped aircraft that sonic boom minimization required. Engine technology had improved as well. While the perfect engine for an SSBJ still didn't exist, manufacturers were working on designs that offered better fuel efficiency, lower noise, and acceptable environmental characteristics. General Electric, Pratt & Whitney, and Rolls-Royce all had concepts for engines that might work in a supersonic business jet application. The engine challenge hadn't been solved, but it looked solvable. Yet despite all these positive developments, no company was willing to launch an actual SSBJ development program. The technical risks were high. The development costs would be enormous, certainly several $billion. The regulatory pathway was unclear, with the FAA having no standards for certifying a supersonic civil aircraft and regulations prohibiting overland supersonic flight. And most critically, there was no proof that sonic boom minimization would actually work in practice. All the theories, all the computational predictions, all the wind tunnel tests were just that: theories and predictions. No one had actually demonstrated a shaped sonic boom with a real aircraft flying through a real atmosphere. This was the situation when DARPA became interested in supersonic aircraft technology. The Defense Advanced Research Projects Agency wasn't bound by commercial concerns or conventional thinking. Its mission was to explore high-risk, high-payoff technologies that might have value for future defense needs. DARPA could invest in basic research and demonstrations that would be too risky for commercial companies. And if DARPA's investments happened to enable civilian applications, that was considered a beneficial side effect. In early 2000, DARPA announced a new program. It was called the Quiet Supersonic Platform, and it would bring together the best minds in supersonic aeronautics, provide government funding to explore cutting-edge technologies, and potentially produce the demonstration that would finally prove whether Richard Seebass's theories could work in practice. The stage was set for the most comprehensive effort yet to solve the sonic boom problem. Meanwhile, at NASA, the High-Speed Research Program. Before we dive into the Quiet Supersonic Platform program, we need to understand what NASA had been doing in the years leading up to QSP. The lessons learned from NASA's ambitious high-speed research program would directly inform DARPA's approach, and many of the people, technologies, and findings from HSR would flow into QSP. The HSR program represented a massive, coordinated effort to develop supersonic transport technology, and its eventual cancellation left a gap that QSP would partially fill. NASA's high-speed research program officially began in 1990, though its roots went back several years earlier. In 1989, NASA and various industry partners had been investigating the feasibility of developing a second-generation supersonic transport that could avoid the problems that had doomed the American SST program in the 1970s. By 1990, the concept had converged on a specific vision: a 300-passenger aircraft capable of cruising at Mach 2.4, designed to be both environmentally acceptable and economically viable. The goals were ambitious. The high-speed civil transport, as the aircraft concept was called, would cross the Atlantic or Pacific in half the time of subsonic jets. It would be fuel-efficient enough to operate profitably. It would meet all environmental standards for noise and emissions, and crucially, it would somehow address the sonic boom problem sufficiently to allow at least some overland supersonic operations. If all these goals could be met, the market potential was enormous. Estimates suggested more than 500 HSCT aircraft could be sold between 2000 and 2015, representing over $200 billion in sales, and potentially creating 140,000 new jobs. The HSR program was structured in two phases. Phase 1, running from 1990 to 1995, focused on developing technology concepts for environmental compatibility. This phase examined fundamental questions. Could engine noise be reduced enough to meet airport noise standards? Could emissions be controlled to avoid harming the ozone layer? Could the sonic boom be minimized enough to allow overland routes? What materials and structures would be needed to withstand the heat of sustained Mach 2.4 flight? Phase 2, beginning in 1995 and continuing through 1999, aimed to demonstrate the environmental technologies and other high-risk technologies needed for economic viability. This phase involved actual hardware development and testing where possible. NASA worked closely with Boeing, McDonnell Douglas, General Electric, Pratt and Whitney, and numerous other contractors and research organizations. The program had strong support within NASA and from parts of the aerospace industry that saw supersonic transport as the next logical evolution of commercial aviation. One of HSR's most visible efforts was the work on supersonic laminar flow. Laminar flow, where air flows smoothly over a surface in orderly layers rather than turbulent eddies, dramatically reduces friction drag. At supersonic speeds, achieving laminar flow is actually somewhat easier than at subsonic speeds, but it still requires very smooth surfaces and carefully designed wing shapes. To test laminar flow concepts, NASA borrowed two F-16XL aircraft from the Air Force and fitted them with special wing gloves designed to maintain laminar flow at supersonic speeds. The F-16XL had been developed in the early 1980s as a proposed variant of the F-16, featuring a cranked arrow wing that gave it exceptional range and payload. Two prototypes were built, but not selected for production, and they eventually went to NASA for research purposes. The XL's wing shape was similar to what an HSCT wing might look like, making it an ideal testbed. NASA equipped the aircraft with extensive instrumentation and special coatings, then flew numerous supersonic test missions to validate computational predictions about laminar flow. The results were encouraging. The tests showed that laminar flow could indeed be maintained over significant portions of the wing at supersonic speeds, confirming the computational design methods. The drag reductions were substantial, potentially improving fuel efficiency by 15 to 20%. This was critical for HSCT economics, as fuel consumption was one of the biggest operational cost drivers. The F-16XL tests provided valuable data that would influence supersonic aircraft design for years to come. Another major HSR initiative addressed the cockpit visibility problem. The Concorde had used a drooping nose that hinged downward for takeoff and landing, giving pilots adequate visibility over the long, pointed nose. But the droop nose added weight, complexity, and maintenance requirements. NASA explored an alternative, an external vision system that would replace windows with cameras and displays. Pilots would fly using synthetic vision presented on screens, with the computer system integrating inputs from multiple cameras, enhanced vision sensors, and synthetic terrain databases. The concept was radical, but it offered significant advantages. Without windows, the fuselage could be stronger and lighter. The cameras could provide better visibility than windows in some conditions, with infrared and other sensors seeing through haze and darkness. The system could overlay flight data, terrain information, and traffic alerts directly onto the visual display. While this technology wasn't mature enough for implementation in the 1990s, the HSR work advanced the concepts and proved feasibility. Today's aircraft increasingly use synthetic vision systems, partly thanks to this early HSR research. Materials and structures received intensive study. At Mach 2.4, aerodynamic heating raises surface temperatures to levels that would weaken or melt aluminum, the traditional aircraft structural material. The Concorde had used aluminum by keeping its speed to Mach 2.0, but Mach 2.4 required different materials. The HSR program investigated titanium alloys, which could handle higher temperatures while maintaining strength. They also developed novel forms of carbon fiber composites that remained stable at elevated temperatures. Testing these materials under realistic conditions required extensive work. NASA built special test facilities that could subject material samples to the thermal cycles they would experience in service. The agency conducted over 13,000 hours of tests, subjecting samples to temperature extremes while monitoring for degradation. The findings guided material selection and showed that a titanium primary structure with advanced composites in secondary structures would likely be the best approach for an HSCT. Engine development was perhaps the most challenging aspect of the HSR program. The engines needed to be powerful enough to accelerate a 700,000 pound aircraft to Mach 2.4 and maintain that speed efficiently. They needed to be quiet enough during takeoff and landing to meet increasingly stringent FAA noise regulations. They needed to produce low emissions, particularly of nitrogen oxides that could potentially damage the ozone layer, and they needed to be economically viable to manufacture and maintain. General Electric and Pratt & Whitney both worked on advanced engine concepts. The designs generally featured variable geometry that could change the engine's characteristics for different flight phases. During takeoff, the engines would operate in a high bypass mode for maximum thrust with lower noise. During supersonic cruise, they would transition to a low bypass mode for efficiency. The technical challenges were immense, requiring advances in materials, cooling systems, combustor design, and control systems. The engine research produced significant advances and valuable data, but it also highlighted the difficulties. Achieving acceptable noise levels while maintaining the thrust needed for supersonic flight proved extremely difficult. The weight of noise suppression systems could easily add 6,000 to 7,000 pounds per engine, equivalent to the weight of 80 to 90 passengers. This penalty significantly impacted the aircraft's economics. Without major breakthroughs in propulsion technology, the HSCT would struggle to be competitive with subsonic aircraft. And then there was the sonic boom. As the HSR program progressed, researchers devoted increasing attention to understanding and potentially minimizing the boom. They conducted human response studies to better understand what boom characteristics people found acceptable. They improved computational methods for predicting sonic boom propagation through the atmosphere. They refined techniques for shaping aircraft to modify the near-field pressure signature. Dominic Maglieri, a veteran sonic boom researcher who had been studying the phenomenon since the 1960s, was deeply involved in the HSR sonic boom work. Maglieri and his colleagues conducted extensive literature reviews, analyzed decades of data, and performed new studies. They worked to understand how boom signatures evolved as they propagated from cruise altitude to ground level, how atmospheric conditions affected this propagation, and how indoor structural response contributed to annoyance. The HSR program also conducted simulator studies where subjects were exposed to recorded sonic booms of different characteristics while performing various tasks or attempting to sleep. These studies attempted to quantify acceptability. What level of boom could 95% of people tolerate? How did the shape of the signature affect subjective response? Were there ways to minimize indoor vibrations separately from outdoor noise? The findings suggested that a properly shaped sonic boom with a peak overpressure around 0.3 to 0.5 pounds per square foot might be acceptable to most people, particularly if it didn't occur repeatedly at regular intervals. A flattened signature with gradual pressure changes would be less startling than a sharp N wave. But achieving these characteristics with a large, heavy HSCT appeared extremely difficult, if not impossible. The HSR program also included an unexpected international collaboration that became one of its most interesting chapters. In the early 1990s, Russia's Tupolev Design Bureau, facing economic hardship after the Soviet Union's collapse, proposed using their Tu-144 supersonic transport as a flying testbed for HSR research. The Tu-144, often called the Concordski, due to its resemblance to the Concorde, had only flown commercially for a brief period in the 1970s before being withdrawn from service. After diplomatic negotiations through the Gore-Chernomyrdin Commission, which fostered US-Russian cooperation in science and technology, NASA agreed to a joint program. Tupolev would modify one Tu-144 aircraft, designated Tu-100, 44LL, for Letaishchaya Laboratoria, or Flying Laboratory, as a research platform. Boeing would lead a team of US industry partners in planning and conducting experiments. The Russian government would support the effort as a way to keep its aerospace industry engaged and to earn hard currency. The Tu-144LL flew its first research flight in 1996. Over the next several years, it completed 27 research flights, gathering data on engine performance, aerodynamics, structural heating, cabin acoustics, and handling qualities. Despite some technical challenges and the general difficulties of the post-Soviet era, the program was remarkably successful. US engineers got to work with actual supersonic transport hardware and collect flight data that would have been impossible to obtain otherwise. Russian engineers earned income and maintained their expertise. It was a genuine win-win collaboration, but as the HSR program continued through the late 1990s, reality began to intrude on the optimistic vision. The economics were proving more challenging than hoped. The sonic boom problem looked no closer to solution despite years of research. Environmental concerns about high-altitude emissions remained contentious, and most critically, the US aerospace industry's interest was waning. Boeing, which had merged with McDonnell Douglas in 1997, was increasingly focused on its next-generation 737 and the proposed 777-200LR, both subsonic aircraft addressing existing market demands. The company's commercial transport division saw limited near-term market for a supersonic transport, particularly one restricted to overland subsonic operation. The development costs for an HSCT would be staggering, probably $15 to $20 billion. Without strong industry commitment to pursue production, the HSR program's value diminished. In 1999, NASA made the decision to wind down the HSR program. Phase 2 efforts were completed or brought to conclusions, but no Phase 3 was initiated. The planned technology readiness date of 2002, which would have supported an industry decision on whether to proceed with actual HSCT development, was abandoned. The Tu-144LL conducted its final research flights in 1999 and the aircraft was retired. After nearly a decade and an investment of well over $1 billion, the HSR program ended without producing a path to an actual supersonic transport. The program's cancellation was disappointing, but not entirely surprising. The HSR had accumulated an enormous amount of valuable research data. It had advanced technologies in aerodynamics, materials, propulsion, and systems. It had trained a generation of engineers in supersonic flight challenges, but it had also confirmed what many suspected. Building an economically viable large supersonic transport remained beyond the reach of available technology, at least for civilian applications where government subsidies weren't available. However, the HSR program left an important legacy. All that research data, all those computational methods, all that accumulated expertise didn't disappear. NASA's research centers, particularly Langley and Glenn, retained the knowledge and capabilities. Industry partners had developed advanced tools and techniques, and critically, the HSR work had made clear that if supersonic civilian flight was going to become practical, it would probably be with smaller aircraft rather than large transports. This realization helped set the stage for DARPA's Quiet Supersonic Platform program. The QSP would build directly on HSR foundations, using computational methods developed during HSR, drawing on sonic boom research conducted for HSR, and even employing some of the same researchers who had worked on HSR. But QSP would take a different approach, focusing on smaller aircraft and emphasizing the sonic boom demonstration that HSR had never attempted. The HSR program's end wasn't the end of the story. It was a transition to a new chapter. Enter DARPA. The Quiet Supersonic Platform is born. The Defense Advanced Research Projects Agency occupies a unique position in the American defense establishment. Unlike the military services, which focus on fielding and operating current weapon systems, DARPA's mission is to explore future capabilities. The agency invests in high-risk, high-payoff technologies that might not bear fruit for years or even decades. DARPA funded the research that led to the Internet, stealth aircraft, GPS, and numerous other transformative technologies. Its small staff of program managers has remarkable freedom to pursue innovative ideas, even those that might seem unlikely to succeed. In early 2000, DARPA became interested in supersonic aircraft technology for several reasons. The Air Force was beginning to think about long-range strike capabilities for the 21st century. Current bombers like the B-52, B-1 and B-2 were subsonic or capable of only brief supersonic dashes. A long-range supersonic bomber could strike targets more quickly, reduce exposure to defenses, and provide greater operational flexibility. There were also potential applications for high-speed reconnaissance aircraft and for transports that could rapidly deliver critical equipment to forward operating locations. But perhaps the most intriguing possibility was that advances in supersonic aircraft technology, particularly in sonic boom reduction, could enable new civilian capabilities. A supersonic business jet wasn't directly a defense application, but the technology developed for such an aircraft might have military benefits. And given the potential commercial market, perhaps industry would be willing to cost-share development, stretching DARPA's limited resources further. The sonic boom problem in particular was arguably more critical for civilian aviation than for military applications, since military aircraft could already fly supersonic in designated training areas. The initial impetus for what became the QSP program appears to have come partly from industry lobbying, particularly by Lockheed Martin and Gulfstream, which had been working together on low-boom supersonic aircraft concepts. These companies approached NASA seeking support, but found that NASA, having just concluded the expensive HSR program, had limited appetite for another major supersonic initiative. The companies then approached DARPA, which was more receptive. The program also benefited from congressional support. Senator Ted Stevens of Alaska, a powerful figure on defense appropriations, secured funding through an earmark in the defense budget. Whether Stevens was motivated by constituent interests, aerospace industry lobbying, or genuine belief in the technology's importance, his support was crucial. The initial funding level was modest by defense standards, about $35 million for fiscal years 2001 and 2002, but it was enough to launch a serious research program. In February 2000, DARPA publicly announced the Supersonic Aircraft Noise Mitigation Program in its portion of the Department of Defense's fiscal year 2001 budget request. The program name would soon change to the Quiet Supersonic Platform, a designation that better captured DARPA's focus. The budget documents described a program directed toward development and validation of critical technology for long-range advanced supersonic aircraft, with substantially reduced sonic boom, reduced takeoff and landing noise, and increased efficiency. The stated goals were ambitious. The program would explore ways to achieve supersonic flight over land without adverse sonic boom consequences, with boom overpressure of less than 0.3 pounds per square foot. The target aircraft would have an unrefueled range approaching 6,000 nautical miles, a gross takeoff weight approaching 100,000 pounds, and significantly lower operational costs than existing supersonic aircraft. To achieve these goals, the program would examine highly integrated vehicle concepts, advanced airframe technologies to minimize sonic boom and drag, natural laminar flow, innovative structural materials, and even more exotic approaches like plasma generation and particle injection. To manage the QSP program, DARPA selected Richard W. Lesien, who came from NASA Langley, where he had been working on micro-adaptive flow control technologies. Lesien's background in fluid dynamics and flow control made him well suited to oversee a program focused on managing the complex aerodynamic phenomena that create sonic booms. He brought both technical depth and program management experience, and he would prove to be an energetic and effective program manager. Walesian and his team at DARPA quickly moved to structure the program and engage potential participants. They identified 3 types of organizations they needed to involve. First, major aerospace corporations capable of serving as system integrators, companies with the resources and expertise to conceive, design, and analyze complete aircraft systems. Second, specialized technology companies and research institutions that could develop specific capabilities like advanced propulsion systems, novel boom reduction techniques, or improved computational methods. And third, universities that could conduct fundamental research and train the next generation of supersonic aeronautics engineers. On March 28, 2000, DARPA hosted an Advanced Supersonic Platform Industry Day in Alexandria, Virginia. The announcement, released a month earlier, made clear that DARPA wanted to facilitate the formation of strong teams and business relationships in order to develop competitive responses to the program. Interested parties were informed that a request for information would be forthcoming, followed by formal solicitations for proposals. The Industry Day attracted significant attendance. Boeing, Lockheed Martin, and Northrop Grumman sent representatives, as did engine manufacturers, materials companies, and various technology specialists. University researchers attended, as did representatives from NASA research centers. The atmosphere was one of excitement mixed with skepticism. The goals were ambitious, perhaps unrealistically so. The budget was modest. The timeline was compressed. But the opportunity to work on supersonic aircraft technology, with DARPA funding and a clear focus on sonic boom reduction, was attractive to many. During the spring and summer of 2000, as DARPA refined its solicitation, Program Manager Richard Seebass sought advice from experts in the field. He met with Peter Cohen from NASA Langley, who had been heavily involved in HSR sonic boom research. He consulted with Dominic Maglieri and Percy Bobbitt from Eagle Aeronautics, both veteran sonic boom researchers. These consultations helped shape the program's technical approach and emphasis. Maglieri and Bobbitt in particular planted seeds that would prove important. Years earlier, during the HSR program, they had proposed using a remotely piloted Firebee drone as a testbed to demonstrate sonic boom shaping with an actual aircraft. The proposal hadn't been funded then, but they revived the idea in their discussions with Walesian. They emphasized that all the computational predictions and wind tunnel tests in the world couldn't fully prove that sonic boom minimization would work until someone actually flew a shaped boom aircraft through a real atmosphere. The physics of shockwave propagation through a variable atmosphere were complex enough that demonstration would be essential for credibility. In August 2000, DARPA issued its formal solicitation for QSP system studies and technology integration. The solicitation made clear that this was not a business-as-usual program. DARPA wanted breakthroughs, not incremental improvements. The program was designed to motivate approaches to sonic boom reduction that bypass incremental business-as-usual approach and is focused on the validation of multiple new and innovative breakthrough technologies. Phase 1 of the program would last approximately 12 months, during which contractors would conduct systems studies, develop conceptual aircraft designs, and assess various boom reduction technologies. The best performers would be selected for Phase 2, which would extend through a second year and involve more detailed technology validation and development. The solicitation emphasized that contractors should be prepared to collaborate and share information in unprecedented ways. DARPA would require the major systems integrators to assess and integrate technologies being developed by specialized contractors, even though these groups were technically competitors. The firm requirement, the one non-negotiable specification that all concepts had to meet, was the 0.3 pound per square foot sonic boom overpressure. This number had emerged from the HSR human response studies and from Seebass's analyses as a threshold that might possibly allow unrestricted supersonic flight over land. It was extremely aggressive, about 1/3 the intensity of a Concorde's boom and lower than any supersonic aircraft had ever achieved. Other specifications were characterized as goals rather than requirements, giving contractors some flexibility. The target cruise speed was Mach 2.4, though lower speeds might be acceptable if other goals could be better satisfied. The gross weight goal was 100,000 pounds, similar to a large business jet. The range goal was 6,000 nautical miles, enough to fly coast to coast in the United States, or to cross the Atlantic with reserves. The aircraft should meet FAA Stage 3 noise standards for takeoff and landing, a significant challenge given the need for high thrust-to-weight ratio. Various other goals addressed fuel efficiency, lift-to-drag ratio, engine performance, and structural weight fractions. As Richard Seebass explained to the trade press, "We have worked with NASA and the US Air Force to come up with numbers which make sense and are self-consistent. In our view, the numbers are reasonable given the state of the technologies, but still well off the projected trend lines." In other words, achieving all these goals simultaneously would require substantial advances beyond the current state of the art. It wouldn't be easy. David Whelan, director of DARPA's Tactical Technology Office, reinforced this message. "We do not see any silver bullet solution, but it might be possible to make improvements in many different areas that add up to a real net improvement." The program structure that emerged divided responsibilities among several categories of contractors. 3 major aerospace corporations would serve as systems integrators, each developing their own conceptual aircraft designs and evaluating all the technologies being researched. Multiple specialized contractors would focus on specific technologies: engine concepts, laminar flow techniques, computational methods, boom mitigation approaches. Universities would conduct fundamental research on particularly challenging problems, and NASA would provide modeling capabilities, wind tunnel facilities, and eventual flight test support. NASA's involvement was important for several reasons. The agency had accumulated extensive supersonic research data and capabilities through the HSR program and earlier efforts. NASA's wind tunnels and computational facilities were world-class. The agency's research centers employed many of the nation's leading supersonic aerodynamicists. And NASA had the flight test capabilities at Dryden Flight Research Center that would be essential if the program progressed to demonstrations. NASA Administrator Dan Goldin enthusiastically endorsed the QSP approach, seeing it as a more focused and practical follow-on to HSR. Throughout the fall of 2000, companies and research organizations prepared their proposals for QSP Phase 1. The 3 major aerospace corporations that would serve as systems integrators assembled their teams, formed partnerships with specialized contractors, and developed their initial concepts. On November 7, 2000, DARPA awarded the first contract, $2.5 million to Northrop Grumman's Air Combat Systems Integrated Systems sector. Shortly thereafter, contracts went to Lockheed Martin's Skunk Works and to Boeing's Phantom Works. The stage was set for an intensive year of conceptual design and technology assessment. The Quiet Supersonic Platform program had officially begun. Over the coming months, these teams would explore the boundaries of what was possible, pushing the limits of aeronautics, propulsion, materials, and computational methods. They would compete with each other while also sharing information in ways that were unusual for the aerospace industry. And they would work toward answering the fundamental question that had stymied supersonic aircraft development for decades. Could the sonic boom be reduced enough to allow supersonic flight over populated areas? Northrop Grumman steps up, building the QSP team. When DARPA awarded the first QSP systems integration contract to Northrop Grumman on November 7, 2000, it might have seemed like an unusual choice to industry observers. Northrop Grumman hadn't been one of the major participants in the NASA HSR program. Neither Northrop nor Grumman, before their 1994 merger, had ever submitted designs for the original supersonic transport competition in the 1960s. The corporation had no recent experience with supersonic passenger or business aircraft. Their expertise was primarily in military systems, particularly advanced fighters and bombers. But Northrop Grumman had unique capabilities that made them an interesting QSP participant. The company had extensive experience with supersonic aircraft through programs like the F-5 fighter family, the YF-23 Advanced Tactical Fighter Demonstrator, and the B-2 bomber. They understood supersonic aerodynamics and had access to some of the most sophisticated computational design tools in the aerospace industry. Their culture emphasized advanced technology and unconventional solutions, and perhaps most importantly, they were hungry for the work. The story of Northrop Grumman's QSP participation began even before DARPA formally announced the program. In January 2000, Charles W. Boccadoro, a future strike systems manager at Northrop Grumman's Integrated Systems Sector in El Segundo, California, had presented a study to Air Force headquarters examining concepts for next-generation supersonic strike aircraft. This was internal research, but it happened to align closely with what DARPA would soon announce as the QSP program. On March 1, 2000, the day after DARPA issued its invitation to the Industry Day, Boccadoro flew to Washington to meet with Richard Lezian. He brought his strike aircraft study and discussed how Northrop Grumman's expertise might apply to the emerging program. Lezian was receptive. At the end of March, 4 other Northrop Grumman officials attended DARPA's Industry Day, including Steve Comodina, who would later become the QSP program's chief engineer and deputy program manager. Boccadoro, a graduate of MIT and the von Karman Institute for Fluid Dynamics, had joined Northrop in 1980 and worked on some of the company's most advanced programs. He had been involved in the B-2 stealth bomber development and the YF-23 Advanced Tactical Fighter, both projects that pushed the boundaries of aerospace technology. His experience with complex aircraft systems and advanced aerodynamics made him an ideal program manager for QSP. In May 2000, he was given additional duties as Northrop Grumman's QSP program manager, with Comodina as chief engineer. One of Boccadoro's first actions was to appoint Joseph W. Pawlowski to lead a small team developing the company's response strategy. Pawlowski was an experienced systems engineer who had worked on multiple advanced aircraft programs. His role would be to coordinate technical activities among various subcontractors and specialists, a critical function given the collaborative nature that DARPA envisioned for QSP. In July 2000, Northrop Grumman hosted its own Industry Day, seeking partners and specialized contractors who could contribute to a QSP proposal. This was a smart strategic move. While Northrop Grumman had deep expertise in military aircraft, they recognized their limitations in areas like business jet design, civilian certification requirements, and the commercial aviation market. They needed partners who could fill these gaps. The partnership that emerged was a clever combination of complementary capabilities. Raytheon Aircraft Company, the Wichita-based subsidiary of Raytheon Corporation that manufactured Beechcraft and Hawker business jets, joined as the primary subcontractor focused on civilian applications. Raytheon brought business jet expertise and commercial market knowledge that Northrop Grumman lacked. As Boccadoro later explained, they will be working principally the civil applications and will be working principally the military applications. But the most shrewd move was hiring Eagle Aeronautics and Weil Laboratories as subcontractors in August 2000 after the July Industry Day. These two companies brought decades of sonic boom research experience. Dominic Maglieri, who had been studying sonic booms since the 1960s, was part of the Eagle Aeronautics team. Between them, Eagle and Weil had compiled more sonic boom knowledge than any other private organizations. They had access to extensive databases, had developed specialized analysis tools, and understood the subtleties of shockwave propagation better than almost anyone. This combination, Northrop Grumman's supersonic aircraft experience, Raytheon's business jet expertise, and Eagle-Weil's sonic boom knowledge, created a strong foundation. The team also established partnerships with engine manufacturers, General Electric and Pratt & Whitney, enlisted MIT's gas turbine laboratory for advanced propulsion concepts, and worked with Stanford University on computational sonic boom prediction methods. Northrop Grumman's approach to QSP reflected the company's engineering culture. Rather than starting with a preconceived aircraft configuration, the team planned to explore a wide design space, evaluating many possible concepts using advanced computational methods. They would leverage multidisciplinary optimization techniques, allowing the computer to search for configurations that best satisfied the multiple competing requirements. The sonic boom requirement would be central to every design decision from the very beginning, not something added later. The team submitted their QSP proposal to DARPA on September 29, 2000. 2 months later, they received word that they had won one of the 3 systems integration contracts. The award was $2.5 million for Phase 1, covering approximately 12 months of work. It wasn't a huge contract by defense industry standards, but it was enough to fund a serious conceptual design effort with a team of talented engineers and specialized consultants. The work began immediately. The initial focus was on what DARPA called system scoping, exploring the overall design space, understanding the key trades and constraints, and identifying promising configurations and technologies. Every aspect of the aircraft had to be considered: the wing shape and placement, the fuselage geometry, the engine type and location, the materials and structure, the fuel system, the control systems. Each choice affected multiple performance parameters and interacted with other choices in complex ways. The sonic boom constraint was particularly challenging. Almost every aspect of aircraft design affected the boom signature in some way. The nose shape was critical. It created the initial shock wave that would become the front of the N wave. The wing placement, sweep, and loading distribution affected where and how strongly the wing shocks formed. The engine inlet and exhaust flows created additional pressure disturbances. The aft fuselage shape influenced the rear shock. Even small details like antennas, sensors, and access panels could perturb the carefully shaped pressure field. To design an aircraft with a 0.3 PSF boom required unprecedented precision in shaping. The team needed to predict the near-field pressure distribution around the aircraft with great accuracy, then model how those pressures would propagate through thousands of feet of atmosphere to reach the ground. Any errors in prediction could mean the difference between success and failure. This drove heavy investment in computational fluid dynamics and boom propagation codes. Northrop Grumman's engineers began with the computational tools they had used on previous supersonic programs, but quickly found these weren't adequate for the QSP challenge. They needed higher fidelity CFD codes that could resolve shock waves more accurately. They needed better boom propagation codes that could handle real atmospheric conditions with wind shear, temperature gradients, and humidity variations. And they needed to integrate these analysis tools into an optimization framework that could rapidly evaluate thousands of design variations. The team worked with their partners at Stanford University, which had been developing advanced sonic boom prediction methods. They collaborated with NASA Langley, which had decades of experience with CFD codes for supersonic flow. they drew on Weil Laboratories' expertise in atmospheric propagation modelling. The result was a suite of computational tools more sophisticated than had been available during the HSR program, capable of predicting sonic booms with unprecedented accuracy. As the design work progressed, certain configuration concepts emerged as promising. One early finding was that placing the engines above the wing and fuselage, rather than in the traditional underslung position, could significantly help with boom reduction. The engines could be positioned to shield the ground from inlet shock waves, and their exhaust could be arranged to minimize impact on the signature. This top-mounted engine configuration became a signature feature of Northrop Grumman's QSP concepts. Another key finding was that a joined wing or strut-braced wing configuration offered advantages. In this unconventional layout, the main wings were supported by smaller forward-swept wings extending from the rear fuselage. This created a structural connection that allowed the main wings to be thinner and more flexible while maintaining strength. Thinner wings generated weaker shock waves, helping with both boom reduction and wave drag. The configuration looked unusual, but the performance benefits were significant. The team also focused heavily on laminar flow. Achieving natural laminar flow over large portions of the wing would dramatically reduce friction drag, improving fuel efficiency and range. At supersonic speeds, maintaining laminar flow is easier than at subsonic speeds in some ways, because the boundary layer is thinner. But it still required very smooth surfaces and careful design. Northrop Grumman worked with Arizona State University on concepts for distributed surface roughness that could suppress cross-flow instabilities and help maintain laminar flow. Boccadoro was adamant that exotic or unproven technologies weren't necessary. A key finding of our studies, he later stated, was that the QSP goals could be achieved without active or exotic sonic boom reduction technologies. The team had evaluated ideas like plasma generation, particle injection, and thermal keels, all concepts that had been proposed as ways to manipulate shock waves, but they concluded that proper aircraft shaping, using well-understood aerodynamic principles, could achieve the goals without resorting to speculative technologies. This was actually an important finding for the QSP program overall. If exotic technologies were required, the path to practical aircraft would be much longer and more uncertain. But if conventional, albeit very advanced, aerodynamics, propulsion, structures, and systems could achieve the goals, then the technologies were more likely to be implementable in actual aircraft within a reasonable time frame. By January 2001, all 16 of the QSP Phase 1 contracts had been awarded. In addition to the 3 systems integrators, DARPA had selected contractors for engine concepts, General Electric and Pratt & Whitney, specific propulsion technologies, Aerodyne, Honeywell, Techsburg, MIT, laminar flow research, directed technologies with Reno Aeronautics, Arizona State University, sonic boom computational methods, Stanford, University of Colorado, and various other specialized areas. Each contractor would work on their assigned technology, but all were expected to share results with the systems integrators. This collaborative structure was unusual for the defense industry, where companies typically guard their proprietary methods and findings closely. But DARPA made it a condition of participation. The systems integrators had to evaluate and integrate technologies from all the specialized contractors, not just from their own partners. This created a more open research environment than was typical, though companies still protected their most sensitive intellectual property. The first 3 months of Phase 1 were devoted to scoping studies. By the end of this period, in early 2001, the technology and propulsion contractors provided their initial findings to the systems integrators. The 3 major contractors, Northrop Grumman, Boeing, and Lockheed Martin, also shared the results of their own sonic boom mitigation studies with each other, an unusual level of cooperation among competitors. For the remaining 9 months of Phase 1, the work intensified. The systems integrators refined their aircraft designs while completing technology evaluation reports. The specialized sonic boom contractors completed their own technology evaluation reports. The propulsion contractors, after finishing their 6-month scoping studies, began working on integrating engine concepts into the overall aircraft designs. Throughout 2001, the QSP team at Northrop Grumman iterated through numerous design variations. Each design cycle involved generating a new configuration, analyzing it with CFD to predict the near-field pressures, propagating those pressures to the ground using boom prediction codes, evaluating the boom signature against the 0.3 PSF goal, and then modifying the design based on the results. It was a computationally intensive process, but the rapid iteration allowed the team to converge on increasingly refined concepts. By the end of 2001, Northrop Grumman had examined 12 different aircraft configurations during Phase 1, ranging from relatively conventional to quite radical. They had evaluated different wing types, various engine positions, multiple nose and tail configurations, and different structural approaches. From this broad exploration, they identified a preferred system concept that met the QSP goals: a joined wing design about 156 feet long with a 58-foot wingspan, top-mounted engines, and extensive use of laminar flow. The team submitted their Phase 1 final report to DARPA on December 12, 2001. The report documented their entire design exploration process, described their preferred concept in detail, identified the key enabling technologies, and outlined what would be needed to progress to an actual aircraft. It represented the culmination of 12 months of intensive work by a team of perhaps 50 core engineers and scientists, supported by specialists at partner companies and research institutions. But even as this Phase 1 effort was concluding, something else was happening that would become the most visible legacy of the QSP program. The theoretical sonic boom work needed validation. The computational predictions needed to be proven, and there was growing consensus that a flight demonstration was essential. Northrop Grumman, with its newly acquired sonic boom expertise from Eagle Aeronautics and Weil Laboratories, was about to propose something ambitious: actually flying an aircraft modified to produce a shaped sonic boom and measuring whether the predictions held true. This would become the shaped sonic boom demonstration, and it would ultimately prove that everything Seebass and George had theorized decades earlier was correct. The historic demonstration, proving theory in flight. By early 2001, about 6 months into the QSP Phase 1 effort, a consensus was emerging among program managers and technical experts that computational predictions alone weren't sufficient. The QSP program had made significant progress in refining sonic boom prediction tools and exploring aircraft configurations that could potentially achieve the 0.3 PSF overpressure goal. But all of this work was based on computer models, wind tunnel tests, and mathematical theory. No one had actually demonstrated that a shaped sonic boom signature would persist as it propagated through thousands of feet of real atmosphere to reach the ground. The question of persistence was critical. Computational codes made simplifying assumptions about atmospheric conditions. Wind tunnels couldn't fully replicate the complexities of real atmospheric propagation over long distances. Even the most sophisticated models had uncertainties. What if there were physical phenomena that the models didn't capture? What if atmospheric turbulence disrupted the carefully shaped signature as it propagated downward? Without an actual flight demonstration, there would always be doubt about whether sonic boom minimization would really work in practice. Richard Seebass, DARPA's QSP program manager, became convinced that a demonstration was necessary. In March 2001, he solicited ideas for how to prove persistence of a shaped boom signature. 3 approaches were considered: flying 2 NASA F-18s in a special formation, modifying a recoverable Firebee drone, or modifying an F-5E fighter aircraft. Each had advantages and disadvantages. The F-18 formation concept was elegant in theory. Fly 2 F-18s very close together in a carefully controlled formation, with one slightly behind and below the other. The combined shock waves from the 2 aircraft might produce a modified signature different from a single aircraft's N wave. But this approach had serious practical problems. Maintaining the required formation accuracy would be extremely difficult. Any deviation would change the signature, and the range of boom modifications possible would be limited. The Firebee concept was more flexible. These remotely piloted target drones had been used for decades and were relatively inexpensive. One could be modified with a new nose and aft section to produce a shaped boom, then flown on multiple test missions. Being unmanned, it could be flown over ground sensor arrays without risk to pilots. The main disadvantage was that Firebees were small and relatively slow compared to a potential supersonic business jet, so the boom characteristics wouldn't be fully representative. The F-5E option was the most ambitious but potentially the most valuable. The F-5 was a small, lightweight supersonic fighter that had been in service since the 1960s. Its size and weight were similar to what a supersonic business jet might be. It could easily reach supersonic speeds at the altitudes of interest. Most importantly, the F-5's modular construction meant that its forward fuselage could be replaced with a modified section designed to produce a shaped boom signature. This would provide the most realistic demonstration of what an actual low-boom aircraft might achieve. Dominic Maglieri and Percy Bobbitt from Eagle Aeronautics had been advocating for a demonstration flight since before the QSP program began. They had proposed a Firebee-based demonstration during the HSR program years earlier. Now, working as part of Northrop Grumman's QSP team, they renewed their advocacy with more detailed proposals. In March 2001, they prepared briefing materials for Valesian, outlining the pros and cons of each demonstration approach. In April 2001, DARPA formally solicited proposals for a demonstration of the persistence of shaped sonic booms. Northrop Grumman, leveraging the expertise of Maglieri, Bobbitt, and their colleagues at Eagle Aeronautics, prepared a comprehensive proposal centered on the F-5E modification approach. The proposal detailed how they would design the modified fuselage, predict the resulting sonic boom, conduct the flight tests and measure the results both on the ground and in the air using chase aircraft. In July 2001, DARPA selected Northrop Grumman's proposal and awarded a contract for what would be called the Shaped Sonic Boom Demonstration. This was separate from the ongoing QSP Phase 1 work, though obviously related. The SSBD would have its own budget, timeline, and set of objectives. It would be managed as a distinct project, though many of the same people would be involved. The SSBD effort brought together an impressive team. Northrop Grumman provided overall program management, systems engineering, and the expertise of their aerodynamics and flight test groups. Eagle Aeronautics and Weil Laboratories contributed their sonic boom analysis capabilities. NASA's Dryden Flight Research Center at Edwards Air Force Base would provide the flight test facilities, instrumentation, and expertise. NASA Langley and other NASA organizations contributed computational support and consultation. The US Navy provided an F-5E aircraft through a cooperative research and development agreement. The first major task was designing the modification. The baseline F-5E had a simple pointed nose, typical of a fighter aircraft. This produced a standard N-wave sonic boom. The goal was to modify the nose and forward fuselage to produce a shaped signature with a lower peak overpressure and, ideally, a flattened waveform instead of the characteristic sharp N-wave spikes. The design process started with defining a target near-field pressure signature, the pressure distribution that would exist immediately around the aircraft. Using Seebass-George theory and advanced optimization methods, the team worked backward from a desired ground signature to determine what near-field pressures were needed. They then designed a nose and fuselage shape that would produce those pressures. This inverse design process required sophisticated computational tools and multiple iterations. The resulting modified nose was dramatically different from the standard F5E nose. It was about 2 feet longer and noticeably more bulbous in certain areas. The shape looked somewhat awkward, not at all like what an aesthetically driven designer would create, but every contour was precisely calculated to generate specific pressure distributions. The nose had an almost pelican-like appearance, with various bumps and curves that controlled how the shock waves would form and strengthen. In addition to the new nose, the SSBD modification required adding sections to the underside of the forward fuselage. These fairings, constructed of aluminum frames and composite skin panels, filled in areas to create the required volume distribution. Again, the shape seemed odd by conventional standards, but each contour served a specific aerodynamic purpose in shaping the sonic boom signature. Before committing to building the full-scale hardware, the team needed to validate their design predictions. They created a 0.05 scale wind tunnel model of the modified F5E and tested it in NASA Glenn's 8 foot by 6 foot supersonic wind tunnel. The sonic boom measurements from the wind tunnel compared favorably with computational predictions, giving the team confidence that their CFD codes and boom propagation methods were working correctly. In April 2003, they would also test a larger model at Mach 2.2 in NASA Ames's 9 foot by 7 foot supersonic wind tunnel, further validating the design. With the design validated, manufacturing of the actual components could proceed. The new nose section and fuselage fairings were fabricated at Northrop Grumman's El Segundo facility. The components were then shipped to Northrop Grumman's St. Augustine, Florida location, where the company performed F5 depot work for the US Navy. There, technicians carefully installed the modified nose and fairings onto the Navy F5E that had been provided for the project. The modification work was meticulous. The attachments had to be strong enough to withstand flight loads, but smooth enough not to disrupt the airflow in unintended ways. Seams between components had to be sealed. Surfaces had to be finished to precise specifications. Any deviation from the intended shape could affect the sonic boom signature, potentially invalidating the demonstration. Quality control was rigorous throughout the manufacturing and installation process. While the aircraft modification was proceeding, planning for the flight test campaign was well underway. The tests would be conducted in the R2515 supersonic corridor at Edwards Air Force Base, the same area where Chuck Yeager had broken the sound barrier in 1947 and where countless subsequent supersonic flight tests had occurred. The corridor was restricted airspace where supersonic flight was permitted, and the vast desert below provided space for ground sensor arrays with minimal background noise. The instrumentation plan was comprehensive. On the ground, 42 microphones and pressure sensors would be arrayed along 2.5 miles under the planned flight path. These instruments, designed and built by NASA Dryden engineers, could precisely measure the pressure time history as the sonic boom passed. The data would show the exact shape of the boom signature and allow comparison with predictions. In the air, NASA's F-15B research aircraft would serve as a chase plane, equipped with a special instrumented nose boom that could measure the shockwave pressures at altitude. The F-15B would fly in the F-5E's shockwave at various distances and positions, mapping out the near-field and mid-field pressure distributions. This in-flight data would be crucial for validating the computational methods used to design the modified nose shape. Additionally, an unmodified baseline F-5E would fly the same profile shortly after the SSBD aircraft, providing a direct comparison. The two aircraft were similar enough that flying them back-to-back on the same flight path, through essentially the same atmospheric conditions, would allow measuring exactly how much the modification changed the boom. This comparison would be powerful evidence of the effectiveness of aircraft shaping. Finally, a US Air Force Test Pilot School L-23 Blahnik glider would fly at a lower altitude beneath the supersonic aircraft, carrying microphones and pressure sensors on its wing and fuselage. The glider would provide an intermediate measurement point between the high-altitude F-5E and the ground sensors, helping to understand how the signature evolved during propagation. The first flight of the modified F-5E SSBD occurred on July 24, 2003, a test flight from St. Augustine to Cecil Field in Florida to verify basic airworthiness and handling qualities. The aircraft then flew cross-country to Palmdale, California, where it underwent further ground tests and preparations. By mid-August, everything was ready for the actual sonic boom measurement flights. August 27, 2003, dawned clear and calm over Edwards Air Force Base. Weather conditions were ideal. Light winds, stable temperature profile, good visibility. The ground crews had deployed all 42 sensors along the measurement corridor during the preceding days, carefully leveling each instrument and verifying communications. The NASA F-15B chase plane and the baseline F-5E were ready. The mission team had rehearsed procedures and verified that all systems were functioning. At the appointed time, Northrop Grumman test pilot Roy Martin climbed into the F-5E SSBD cockpit. He had been thoroughly briefed on the flight profile: climb to 32,000 feet, accelerate to supersonic speed, maintain steady straight flight at Mach 1.4 while passing over the ground sensor array, then decelerate and return to base. The profile had to be flown precisely. Any deviations in speed, altitude, or heading could affect the measurements. As the F-5E SSBD rolled down the runway and lifted off, decades of theoretical work, computational analysis, wind tunnel testing, and engineering development came down to this moment. Would the shaped nose produce the predicted boom signature? Would that signature persist through thousands of feet of atmosphere? Would the measurements on the ground and in the air match the predictions? The flight went smoothly. Martin flew the profile exactly as planned, maintaining the required altitude and speed within tight tolerances. The NASA F-15B, piloted by veteran research pilot Lieutenant Colonel James Less, positioned itself at various stations to measure the shockwave field around the SSBD aircraft. Shortly after the SSBD pass, the unmodified baseline F-5E flew the same profile for comparison. The instrumented glider captured data at intermediate altitude, and all 42 ground sensors recorded the booms as they swept across the desert. Within hours, preliminary data analysis began. Engineers downloaded the recordings from ground sensors and aircraft instruments, processed the data to remove background noise and artifacts, and began comparing measurements with predictions. The results were stunning. The SSBD aircraft had indeed produced a shaped boom signature, significantly different from the standard N-wave. More importantly, that shaped signature had persisted through its propagation from 32,000 feet to ground level. The initial analysis showed that the shaped boom had a peak overpressure about 1/3 lower than the unmodified F-5E flying the same profile. Even more significantly, the waveform shape was markedly different. Instead of the sharp pressure spikes of a classic N wave, the SSBD's signature had a more gradual rise to peak pressure and a flattened top. The sudden pressure changes that make N-wave booms so startling were reduced. The measured signature matched the predictions remarkably well. Over the following days and weeks, the team conducted additional test flights with various slight modifications to the profile, gathering more data and building confidence in the results. They flew 5 sonic boom measurement flights in total, 3 comparing the SSBD to the unmodified F-5E back-to-back, and 2 using the NASA F-15B to measure near-field pressures. Each flight provided valuable data, and the consistency of results across multiple flights was impressive. The in-flight measurements from the F-15B were particularly valuable. By positioning the chase aircraft at different distances and orientations relative to the SSBD, the team could map how the pressure signature evolved during its downward propagation. This data showed that the shaped signature formed close to the aircraft and then maintained its general characteristics as it propagated, exactly as theory predicted. The computational methods used to design the modification were validated as accurate. The achievement was historic. For the first time ever, a flight vehicle had been deliberately modified to produce a shaped sonic boom, and the signature had been measured at the ground to confirm that it differed significantly from a conventional boom. Decades of theoretical work by Seebass, George, and others had been proven correct in actual flight conditions. The laws of physics did indeed allow sonic boom minimization through aircraft shaping, and the effect persisted through a real variable atmosphere. The implications were profound. Prior to SSBD, sonic boom reduction had been theoretical, based on computational predictions that could never be fully validated. After SSBD, it was a demonstrated fact. Aircraft could be shaped to reduce sonic booms. The technology was real, not speculative. This fundamentally changed the discussion about supersonic flight over land from "can it be done?" to "how do we do it practically?" For the QSP program, the SSBD's success validated the entire approach. The computational tools being used by all the QSP contractors had been proven accurate. The sonic boom minimization techniques being incorporated into aircraft designs had been shown to work. The program's focus on boom reduction as an enabling technology for long-range supersonic aircraft was justified. DARPA, NASA, and the contractor teams could proceed with confidence that the fundamental physics were understood and achievable. But SSBD also clarified what remained to be done. The demonstration had shown that a boom could be shaped and reduced, but the F-5E modification produced a boom considerably louder than the 0.3 PSF target. The SSBD aircraft was just a proof of concept, not an optimized low-boom design. It showed that boom shaping worked, but achieving the truly quiet booms needed for unrestricted overland flight would require even more sophisticated aircraft designs. The journey wasn't complete, but a crucial milestone had been achieved. QSP Phase 2 and the path forward. With the shaped sonic boom demonstration proving that boom shaping could work in practice, the quiet supersonic platform program moved into its second phase in early 2002. Phase 2 would involve more detailed design work, technology validation activities, and maturation of the most promising concepts and technologies identified during Phase 1. The program was evolving, with both successes to build on and challenges to address. In May 2002, DARPA announced the Phase 2 contract awards. Northrop Grumman's Integrated Systems sector received $2.7 million to continue validating their QSP concepts. This would include wind tunnel testing of a scale model of their preferred aircraft configuration and working with Raytheon on fabricating and testing structural components made with advanced composite materials. At the same time, DARPA awarded Northrop Grumman an additional $3.4 million contract for continuing the shaped sonic boom demonstration work, which would include additional flights and data analysis. Lockheed Martin's Skunk Works also received a Phase 2 award to continue developing their design concept. However, Boeing's Phantom Works was not selected to continue beyond Phase 1. Boeing had explored some particularly radical configurations during Phase 1, but these hadn't progressed as far as the Northrop Grumman and Lockheed Martin concepts. This downselect to two systems integrators was part of DARPA's plan to focus resources on the most promising approaches. Other Phase 2 contracts went to General Electric for advanced propulsion system development and to Arizona State University to continue their research on distributed roughness for maintaining laminar flow. The program was focusing on technologies that appeared most likely to enable practical aircraft, while de-emphasizing more speculative approaches. An important shift occurred in the program's emphasis around this time. Initially, the 0.3 PEF sonic boom overpressure had been a firm requirement, but by Phase 2, it had been downgraded to being one of several goals, with no single parameter being mandatory. This reflected DARPA's recognition that the multiple goals, low boom, long range, high speed, low weight, efficiency, were in tension with each other. Achieving all of them simultaneously was extraordinarily difficult, perhaps impossible with near-term technology. Rather than insisting on one parameter at the expense of others, DARPA wanted contractors to find the best overall balance. This change also reflected a shift in program focus, more toward military applications. The September 11, 2001 terrorist attacks had refocused attention on military capabilities, and the Air Force was increasingly interested in long-range strike platforms. For military missions, a somewhat louder boom might be acceptable if the aircraft gained capabilities in other areas. A sonic boom of 0.5 PSF, while too loud for unrestricted civilian overland flight, might be acceptable in designated military supersonic corridors or for operations where the benefits outweighed the noise concerns. Throughout 2002, Northrop Grumman's team continued refining their preferred QSP concept. The basic configuration remained a joined-wing aircraft about 156 feet long, with a 58-foot wingspan and top-mounted engines. But countless details were being optimized through additional computational analysis and wind tunnel testing. The wing shapes were refined to improve the pressure distribution. The nose contours were adjusted to minimize the initial shock strength. The aft fuselage was shaped to control the rear shock. Engine inlet and exhaust configurations were optimized for both performance and boom impact. One of the challenges was balancing the boom minimization goal against other requirements. Making the aircraft longer helped reduce the boom according to Seebass's figure of merit, but longer aircraft were structurally heavier and had more wetted area, increasing friction drag. Making the wings thinner reduced wave drag and boom intensity, but made structural design more difficult. Placing engines on top of the fuselage helped with boom shaping, but complicated inlet design and maintenance access. Every decision involved trade-offs. The joined wing configuration offered structural advantages that helped resolve some of these trade-offs. The forward-swept aft wings braced the main wings, allowing them to be thinner and more lightly built while maintaining adequate stiffness. This structural efficiency enabled the long, slender planform that sonic boom minimization required. The configuration did create some aerodynamic complexities at the wing junction points, but computational analysis suggested these could be managed. Engine integration was particularly challenging. The QSP goals required engines that could efficiently propel a 100,000 pound aircraft to Mach 2+, while meeting noise and emissions standards. Variable cycle engines that could operate in different modes for takeoff versus cruise appeared necessary, but such engines were complex, heavy, and expensive. The engine manufacturers participating in QSP, General Electric and Pratt & Whitney were exploring various concepts, but perfect solutions remained elusive. In September 2002, Northrop Grumman publicly unveiled more details about their QSP concept at an industry event. They showed images of their preferred design, a sleek aircraft with the distinctive joined wing configuration and top-mounted engine nacelles. The design featured what they called isentropic inlets, carefully shaped air inlets designed to compress incoming air smoothly without strong shock waves. Extensive laminar flow over wings and fuselage would minimize friction drag. An adaptive leading edge on the wings could optimize the wing shape for different flight conditions. The performance predictions were impressive. The design would cruise at speeds above Mach 2 with a range of 6,000 nautical miles. With careful design and operation, the sonic boom overpressure could be reduced to around 0.5 psf, about 7 times quieter than the Concorde. While not quite achieving the original 0.3 psf goal, this level represented a major advance and might be acceptable for some operational scenarios. Raytheon Aircraft had designed a variant configured as a supersonic business jet, while Northrop Grumman's version emphasized military long-range strike capabilities. In April 2003, Northrop Grumman tested a scale model of their final QSP configuration in NASA Ames's 9-foot by 7-foot supersonic wind tunnel. The test ran for 33 hours at Mach 2.2, measuring forces, pressures, and flow characteristics. The data validated the computational predictions and confirmed that the design would produce the expected aerodynamic performance and sonic boom characteristics. It was a crucial step in proving that the concept wasn't just theoretical, but could actually be built and would work as predicted. Meanwhile, Lockheed Martin's Skunk Works was pursuing its own distinctive approach. Their concept featured a slender fuselage, highly contoured swept wings with underwing-mounted engines, and a V-tail configuration. The design emphasized a sinuous fuselage shape with carefully controlled volume distribution to shape the boom signature. Lockheed was leveraging their decades of experience with advanced supersonic aircraft, including the SR-71 and various classified programs, to push the boundaries of what was possible. Boeing's Phase 1 work, though not continuing into Phase 2 with DARPA funding, had explored perhaps the most radical configurations. Their concepts included thin, unswept wings fore and aft, with a swiveling main wing that could be stowed along the top of the fuselage during supersonic cruise. Natural laminar flow over the thin, unswept wings would minimize drag. The configuration was driven by trying to achieve the absolute minimum wave drag and sonic boom, even if it meant accepting unusual appearance and complexity. Boeing later published technical papers describing their QSP work, contributing to the broader research community's understanding. Richard Lezian moved to NASA headquarters in the fall of 2002, and Stephen H. Walker, assigned to DARPA from Defense Research and Engineering in the Pentagon, took over as QSP Program Manager. Walker would guide the program through its final phases. He later explained that even though the sonic boom goal had been relaxed, what we ended up finding out was that if you improve lift and drag, if you improve specific fuel consumption, if you reduce your empty weight, all these things lend themselves to lower sonic boom as well. In other words, the technologies needed for efficient long-range supersonic flight naturally aligned with boom reduction. The QSP program began to wind down during the first half of 2003. DARPA's biennial budget estimates submitted in February 2003 included $4.8 million for fiscal year 2003, but nothing for fiscal year 2004. The program had accomplished much of what it set out to do: explore technologies for quiet supersonic aircraft, develop and validate computational design methods, demonstrate that sonic boom shaping actually works. and produce detailed conceptual designs that could guide future development efforts. Northrop Grumman submitted its final QSP documentation on May 22, 2003. The submission included extensive technical reports describing every aspect of their design work: aerodynamics, propulsion integration, structures and materials, systems, performance predictions, manufacturing considerations, and cost estimates. Similar documentation came from Lockheed Martin. These reports represented the accumulated knowledge from 3 years of intensive research and development by some of the best aerospace engineers in the world. The results of the QSP program went to the Air Force for use in its ongoing long-range strike platform studies. The Air Force leadership, no longer comfortable with the unambitious projections in their 1999 bomber roadmap, was seeking fresh ideas on future strike capabilities. The service eventually examined more than 20 different proposals from Northrop Grumman, Lockheed Martin, and Boeing for what might become the next generation of long-range bombers. While none immediately led to a development program, the QSP work influenced thinking about what was possible for supersonic aircraft. For Northrop Grumman's engineers, the QSP program provided valuable experience even though it didn't lead directly to production aircraft. The company hadn't had major supersonic projects since the YF-23 Advanced Tactical Fighter in the early 1990s and work on the F/A-18E/F Super Hornet inlets. QSP allowed them to exercise and advance their supersonic design capabilities. The experience helped sustain expertise that would prove valuable for future projects, including DARPA's Switchblade oblique wing study and advanced work with the Air Force Research Laboratory. Perhaps the most significant QSP legacy was proving that shaped sonic booms were real and achievable. The shaped sonic boom demonstration didn't just validate one particular aircraft modification, it validated the entire theoretical foundation. It showed that computational methods could accurately predict sonic booms. It proved that signatures shaped at the aircraft would persist through the atmosphere to the ground. It demonstrated that boom intensity could be significantly reduced through aircraft shaping. All of this changed the equation for future supersonic aircraft development. Legacy and looking forward. The Quiet Supersonic Platform program officially ended in 2003, but its influence continues to this day. The technologies explored, the methods developed, the lessons learned, and the fundamental proof that shaped sonic booms work have informed every subsequent effort to develop quiet supersonic aircraft. In many ways, QSP was a bridge between the theoretical work of the 1960s and 1970s and the practical development efforts of the 21st century. One of the most important legacies of QSP was the advancement of computational design methods. The high-fidelity CFD codes and boom propagation tools developed during the program became the foundation for subsequent supersonic aircraft design efforts. These tools allowed engineers to rapidly evaluate design variations and optimize aircraft shapes for low boom. The accuracy of these predictions, validated by the SSBD flight tests, gave confidence that computer-designed aircraft would actually perform as expected. The QSP work also advanced understanding of the physics involved in sonic boom generation and propagation. While the basic theory had been established decades earlier, QSP provided much deeper insight into the details. How do atmospheric conditions affect boom evolution? What are the practical limits of boom reduction for various aircraft sizes and missions? How do different design features contribute to or mitigate the boom? What level of manufacturing precision is required to maintain intended signatures? All these questions were explored in depth during QSP. The program demonstrated the value of integrated design approaches. Sonic boom couldn't be addressed as an isolated problem. It had to be considered from the very beginning of the design process, alongside all other requirements. This systems-level thinking, which DARPA encouraged through the program's structure, proved essential for achieving the ambitious goals. Future supersonic aircraft programs would need similar integrated approaches rather than trying to add boom reduction as an afterthought. Perhaps most importantly, QSP showed that solving the sonic boom problem was possible, not with exotic or speculative technologies, but with advanced but achievable engineering. This fundamentally changed the discussion about supersonic flight. Before QSP and SSBD, many doubted whether boom reduction could work at all. After QSP, the question became how to optimize and implement boom reduction practically rather than whether it was feasible. The most direct successor to QSP was NASA's N+3 Supersonic Technology Program, which began in the late 2000s and eventually led to the X-59 QSST Quiet Supersonic Technology Program. NASA awarded contracts to Boeing, Lockheed Martin, and Northrop Grumman in 2010 to develop conceptual designs for a low-boom demonstrator aircraft. This work built directly on QSP foundations, using similar computational methods and incorporating lessons learned from the shaped sonic boom demonstration. Lockheed Martin's Skunk Works ultimately won the X-59 contract in 2016. The X-59 design shows clear lineage from QSP concepts: a long, slender fuselage, carefully contoured surfaces, top-mounted engine, and every detail optimized for boom reduction. The aircraft is predicted to produce a boom of 75 perceived decibels or less, quiet enough that NASA plans to fly it over communities to assess public reaction. If successful, the X-59 could help inform changes to regulations that currently prohibit civil supersonic flight over land in the United States. The X-59, if it achieves its goals, will be the ultimate validation of the work that began with Seebass and George's theory, continued through NASA's HSR program, and was dramatically advanced by DARPA's QSP effort. It represents decades of accumulated research and development aimed at solving one of aviation's most persistent problems. First flight is currently planned for the mid-2020s, and community testing could begin shortly thereafter. Beyond government research programs, the commercial sector has also shown renewed interest in supersonic flight, partly inspired by the progress in boom reduction technology that QSP demonstrated. Several startup companies have announced plans for supersonic business jets or small supersonic airliners. Boom Supersonic, Ariane, which unfortunately ceased operations in 2021, Spike Aerospace, and others have proposed designs incorporating low-boom technologies. These commercial efforts face significant challenges beyond the technical ones that QSP addressed. Regulatory certification pathways for supersonic civil aircraft remain unclear. The FAA has begun developing noise standards for supersonic aircraft, but the process is complex and time-consuming. Economic viability is uncertain given the high development costs and limited initial market size. Engine manufacturers have been hesitant to commit to new supersonic engine development without firm aircraft orders. The path from concept to operational aircraft is long and expensive. Gulfstream Aerospace, which was involved in early SSBJ concepts that influenced QSP, continues to research supersonic technologies. The company has been relatively quiet about its specific plans, but patents and occasional statements suggest ongoing work on low-boom supersonic business jets. Gulfstream's Quiet Spike concept, tested on a NASA F-15B in the mid-2000s, demonstrated another approach to boom reduction using an extendable nose spike. While that particular concept had limitations, it showed Gulfstream's continued commitment to solving the supersonic puzzle. The regulatory environment is slowly evolving. The FAA's ban on civil supersonic flight over land is not actually a regulation against speed, but rather against causing boom levels that disturb people on the ground. If an aircraft can prove it produces an acceptably quiet boom, there's potential for the ban to be modified or waived. NASA's X-59 community testing is explicitly designed to gather data that could inform regulatory changes. Similarly, international regulations could evolve if quiet supersonic flight can be demonstrated as practical. There are also military applications for quiet supersonic technologies that emerged from QSP. While the Air Force didn't immediately proceed with a new supersonic bomber, the service continues to study advanced strike concepts. The ability to fly supersonic with reduced boom could allow operations in areas where noise has been a constraint. High-speed reconnaissance aircraft could benefit from lower acoustic signature. Even supersonic drones might use shaped boom technology to reduce their detectability and minimize disturbance during operations. The QSP program demonstrated several broader lessons relevant to government R&D programs. DARPA's approach of setting aggressive goals, funding multiple competing approaches, requiring collaboration among competitors, and focusing on demonstration rather than just analysis proved effective. The program achieved significant advances in a relatively short time with modest funding by encouraging innovative thinking and risk-taking. These management approaches could be applied to other challenging technology development efforts. Looking at what might have been different, some observers have noted that QSP didn't lead directly to an actual aircraft development program. After the successful SSBD demonstration in 2003, there were hopes that Phase 3 might proceed to building a full-scale QSP aircraft, or at least a more comprehensive demonstrator. But funding constraints, shifting priorities, and the inherent challenges of supersonic aircraft development prevented this. The technology maturation stopped short of a complete system demonstration. Part of the challenge was market uncertainty. Without a clear path to operational systems, either military or civilian, it was difficult to justify the enormous expense of building complete aircraft. The Air Force's bomber requirements remained focused on subsonic stealth capability, which eventually led to the B-21 Raider program. No commercial manufacturer was willing to invest the billions needed to develop a supersonic business jet without clearer market demand and regulatory approval. QSP proved the technology was possible, but couldn't solve the market and policy problems. Another question is whether the program's goals were too ambitious. Trying to simultaneously achieve very low boom, long range, high speed, low weight, and efficiency stretched the limits of what was possible. Each goal pushed the design in somewhat different directions, and optimizing for all simultaneously was extremely difficult. Some critics argued that focusing on fewer, more achievable goals might have led to more practical near-term results. But DARPA's mission is to push boundaries, and setting aggressive goals drove innovation even if they weren't all fully achieved. The technology developments from QSP extended beyond just sonic boom reduction. Advances in computational design methods, laminar flow technology, advanced materials and structures, and propulsion concepts have found applications in other aircraft programs. The optimization techniques and integrated design approaches developed during QSP have influenced how supersonic aircraft are designed more broadly. Even programs not directly focused on boom reduction have benefited from QSP's technical legacy. Educational impacts shouldn't be overlooked. Many graduate students and early career engineers worked on QSP-related research at universities and national laboratories. This built expertise in supersonic aerodynamics and acoustic phenomena that might otherwise have been lost as the generation that worked on the original SST efforts retired. Universities strengthened their supersonic research programs. NASA research centers maintained and advanced their capabilities. This human capital development ensures that expertise will be available for future supersonic aircraft efforts. International interest in supersonic flight has grown as well. Japan has continued research on supersonic transport concepts, with particular interest in Pacific routes where supersonic flight offers significant time savings. European research programs have explored supersonic business jets and small transports. Russia has announced concepts for modernizing supersonic transport capabilities. China has revealed research on supersonic aircraft. While none of these international efforts have yet produced operational aircraft, the global interest shows that the promise of supersonic flight remains compelling. Climate and environmental considerations add new dimensions to supersonic aircraft development. Concerns about carbon emissions, high-altitude effects, and sustainability create additional challenges for any future supersonic transport. Aircraft will need to meet increasingly stringent environmental standards, potentially requiring alternative fuels or propulsion systems. These considerations weren't emphasized in QSP, which focused on boom reduction and aerodynamic efficiency, but they're becoming increasingly important for any practical supersonic aircraft program. The dream of routine supersonic passenger flight, flying from New York to London in 3 hours, Los Angeles to Tokyo in 5 hours, cutting intercontinental travel times in half, remains tantalizing but elusive. The Concorde showed it was technically possible, but never economically viable in its fuel-hungry, noise-producing form. Modern technology offers the potential for more efficient, quieter supersonic flight, but challenges remain. Will we see supersonic airliners in our future? Perhaps, but probably not soon, and likely starting with smaller aircraft serving specific high-value routes rather than mass-market transportation. More immediately plausible are supersonic business jets. The market is smaller, but potentially more tolerant of premium prices. A 10 to 12 passenger supersonic business jet that could fly coast to coast in 2 hours rather than 5, or New York to London in 3 hours rather than 7, might find enough wealthy customers to justify production. Several companies are pursuing this market, building on the foundation that QSP helped establish. If regulations can be updated and engines developed, we might see supersonic business jets by the 2030s. The Quiet Supersonic Platform program was a crucial stepping stone in the long journey toward practical supersonic flight over land. It built on decades of prior research, demonstrated key technologies, proved fundamental theory, and laid groundwork for future efforts. While it didn't immediately lead to new aircraft, its legacy lives on in ongoing programs like the X-59, in commercial efforts to develop supersonic business jets, and in the accumulated knowledge that makes future supersonic flight more achievable. The program showed that Richard Seebass's vision was correct. With proper design, the sonic boom could be tamed, and the sky could be opened to faster flight without disturbing the peace below. Conclusion: the sound of progress. We've journeyed through more than 60 years of aviation history, from Chuck Yeager's barrier-breaking flight to the carefully shaped booms of the 21st century. We've seen how the sonic boom problem emerged as commercial aviation eyed supersonic speeds, how it became a political and environmental issue that killed the American SST program, and how dedicated researchers refused to accept it as an insurmountable barrier. We've explored the theoretical work of Richard Seebass and Albert George, the ambitious HSR program, the various attempts to design supersonic business jets, and finally the QSP program that brought everything together. The story of the Quiet Supersonic Platform is ultimately about the long arc of scientific and engineering progress. Problems that seem impossible one decade can become solvable the next, as theory advances, computational capabilities grow, materials improve, and understanding deepens. The sonic boom problem appeared intractable in the 1970s. By the 2000s, through accumulated research and technological progress, it had become manageable, at least for smaller aircraft carefully designed with boom reduction as a primary goal. The August 27, 2003 flight of the shaped sonic boom demonstrator over Edwards Air Force Base was a historic moment. For the first time, an aircraft deliberately modified to produce a shaped boom flew through a real atmosphere and proved that the shaped signature persisted to the ground. Decades of theoretical work were validated. Computational methods were proven accurate. The fundamental feasibility of sonic boom reduction through aircraft shaping was demonstrated beyond question. It was a moment of scientific and engineering triumph, the kind of breakthrough that can enable entirely new capabilities. Yet more than 20 years after that successful demonstration, we still don't have quiet supersonic aircraft flying regularly. The SSBD proved the concept worked, but many challenges remain between proof of concept and operational aircraft. Economics, regulations, engine development, certification pathways, market size, and environmental concerns all pose obstacles. Technology is necessary but not sufficient. Practical supersonic flight also requires market demand, regulatory frameworks, and sustainable business models. The QSP program didn't solve all these problems. It couldn't, given its limited scope and budget. What it did do was remove fundamental technical uncertainty about whether sonic boom reduction was possible. That's valuable progress. It means future supersonic aircraft programs can proceed with confidence that boom reduction can work, allowing them to focus on the other challenges: propulsion, economics, certification, market development, rather than questioning the basic feasibility. We can see QSP's influence continuing today. The NASA X-59 program, with its planned 2020 test flights over communities, follows directly from QSP's foundation. Commercial companies proposing supersonic business jets cite boom reduction technologies, validated during QSP. Regulatory discussions about updating supersonic flight restrictions reference the SSBD demonstration and subsequent research. Academic research programs continue to advance computational methods and design approaches pioneered during QSP. The program's legacy extends far beyond its formal 3-year duration. What does the future hold for supersonic flight? It's hard to say with certainty. Economic and environmental pressures on aviation are intense. Climate change concerns may constrain growth of all air travel, not just supersonic. High fuel prices and emissions restrictions could make supersonic operations difficult to justify. On the other hand, technology continues to advance. Sustainable aviation fuels might enable lower carbon supersonic flight. Advanced engines could improve efficiency. Composite structures could reduce weight. The market for time-saving premium air travel continues to grow. My guess, and it's only informed speculation, is that we'll see supersonic business jets before we see large supersonic airliners. The smaller market, higher price points, and point-to-point operations of business jets align better with near-term technical and regulatory reality than high-volume scheduled airline service. If companies like Boom Supersonic or successors to Aerion can actually bring products to market, and if regulators update the rules to allow quiet supersonic overflight, we might see business supersonic flight regime in the 2030s. Large supersonic airliners comparable to the Concorde face much tougher challenges. The economics are difficult, the environmental impacts larger, the regulatory hurdles higher. Unless there are significant breakthroughs in propulsion efficiency and further boom reduction, mass-market supersonic travel seems unlikely soon. But perhaps by mid-century, with continued technology development and accumulated experience from business jets, larger supersonic transports could become viable for high-density routes where time savings command premium prices. What's clear is that the dream hasn't died. Humans have always wanted to go faster, to shrink distances, to bring far places closer. Supersonic flight offers the potential to make the world genuinely smaller, to make intercontinental trips routine rather than major expeditions, to enable business and personal connections that aren't practical at subsonic speeds. The promise is real, even if fulfillment remains uncertain. The Quiet Supersonic Platform program and the Shaped Sonic Boom demonstration represent humanity's refusal to accept limits. When physics seem to prohibit supersonic flight over populated areas, scientists and engineers work to understand the physics better and find ways to work within natural laws rather than violating them. When conventional wisdom said the boom couldn't be tamed, researchers showed that with sufficient care and design, it could be shaped and reduced. When cynics claimed it wouldn't work in practice, test pilots flew demonstrators and proved the concept. This persistent determination to solve hard problems, to turn impossibility into possibility, is what drives technological progress. It's what took us from the Wright Flyer to orbital spaceflight in barely 60 years. It's what might take us from the sonic boom carpet that grounded supersonic flight to routine quiet supersonic travel around the world. The path is long, the challenges remain significant, but the direction is clear. Richard Seebass, who didn't live to see his theories proven in flight, would surely be pleased to see how his theoretical work has influenced decades of subsequent research. Albert George, his collaborator, would appreciate seeing their jointly developed optimization methods actually applied to real aircraft. The hundreds of engineers, scientists, technicians, and pilots who contributed to QSP and SSBD can take pride in advancing the state of the art and demonstrating what seemed impossible. Their work made the future a little clearer and a little closer. Thank you and stay curious. If you've made it this far, thank you for spending these couple of hours with me exploring the Quiet Supersonic Platform program. I hope you've gained appreciation for the long arc of research and development, the interplay of theory and practice, the collaboration between government, industry, and academia, and the persistent human drive to overcome technical challenges. The story of supersonic flight isn't finished. New chapters are being written as NASA's X-59 progresses toward flight testing, as companies continue developing supersonic business jet concepts, as researchers refine computational methods and design approaches, and as regulators grapple with updating rules written in an earlier era. The dream of routine supersonic flight, deferred but not abandoned after the Concorde's retirement, may yet become reality. I encourage you to follow developments in this field. Watch for news about the X-59's first flight and community testing. Keep an eye on commercial supersonic aircraft efforts. Pay attention to regulatory changes that might enable quiet supersonic operations. The next decade could see significant progress toward making supersonic flight practical and acceptable for civilian use. We might be witnessing the early stages of a transformation in aviation comparable to the jet age revolution of the 1950s and 1960s. If you enjoyed this deep dive into aerospace history and technology, please consider subscribing to the Space Historian channel and liking this video. Your support helps me continue producing these detailed explorations of space and aviation topics. Consider sharing this video with friends who might be interested in aerospace engineering, aviation history, or supersonic flight. The more people understand the technical challenges and the progress being made, the better our collective appreciation for these remarkable achievements. Feel free to leave comments with your thoughts, questions, or corrections. I love hearing from viewers, especially when they have expertise or experiences relevant to the topics we cover. The community that forms around these videos enhances everyone's understanding. If you have suggestions for future topics, please share those as well. There are countless fascinating stories in aerospace history waiting to be told. Until next time, keep looking up, stay curious, and remember that today's impossibilities often become tomorrow's routine operations. The sky isn't the limit, it's just the beginning. This has been Space Historian. Thanks for watching, and I'll see you in the next video.